of the radar range equation, the classical range equation. And part one will also include, as we'll get into in a moment, the derivation of the term called radar cross-section, from which much of radar signature analysis work is done. And from radar cross-section, we'll begin to discuss some of the classic target shapes, such as cylinders, spheres, cones, and flat plates, and protrusion, and so on. And as I mentioned, though, that part one will be more or less introductory. Part one assumes that you, as a student, have had as a background mathematically a good high school education in algebra, some trig, and have at least an acquaintance with logarithms, powers of tens, and so on. We have to start at this level. We feel this would probably be an average background mathematically of most people to whom this course is oriented, which would be the on-site radar technician at most of the, in our case, Air Force Eastern Test Range radar sites, such as the MIPR sites, the TTR site, and as we had in the past, the Trinidad radar system. So the course is oriented principally toward the operations people who actually operate and maintain radar systems, of course. It's also would be very valuable to those who would like to get a understanding of basic radar signature analysis who haven't been exposed to it in the past, or at least a very minimal exposure. So part one pretty much introduces the course and the total content of our course. We'll be rather limited in the depth of analysis we can produce or perform in part one of the radar signature analysis course, because some of the more advanced techniques require a good understanding of orbits, a little bit about orbital mechanics, and the flight path of the various targets that we'll be observing. Now, principally, the targets that we'll be analyzing in the radar signature analysis course, and of course in real time, real practice, will be those targets which are in orbit, orbiting satellites and their associated rocket bodies and various fragments. And in the case of the suborbital flight, re-entering tanks, warheads, decoys, chaff, and other devices which might enter back into the atmosphere that you'd be tasked upon to track and analyze. So part one will introduce the basics. Part two, of which will be several tapes, will deal principally with the subject of orbital mechanics, the ellipse, the various flight paths that objects would take through space. We'll develop these, the basic mathematics involved with them, to a limited degree. We might get a good understanding of flight path. And of course, as we understand the flight path, we must understand the environment in which it's in. And the flight path of the object, of course, is contained within the celestial sphere. So we'll have a little bit on the celestial sphere, celestial mechanics, right ascension, declination, and other factors and terms included in the celestial sphere. We'll relate this to the Earth's coordinate system, longitude and latitude, and along with the rotational rate of the Earth, the inertial stability of the orbit, or the orbiting body, and relate all these together that we might understand how the object might track over the ground on the Earth, and how it would appear through a radar or a point on the ground that would be tracking it. So part two will be principally the flight, orbital mechanics, and of course after we get through with orbital mechanics, we should consider the re-entering case, or the suborbital flight, which we will do. So we'll spend some time in part two on the subject of re-entering into the Earth's atmosphere by a rocket body or nose cone, warhead, and other objects that may be associated with it. Spend some time on re-entry and the associated phenomena. That is, the development of wake, of plasma which surrounds the body and of course constitutes principally the wake. We'll study such things as laminar turbulent flow of the mass about the body, or as the body penetrates the mass or the medium of air. Find out just how this wake re-entry phenomena affect radar signals, radar cross-section, and how we can overcome some of these problems and also use some of this phenomena to our advantage. So again, part one will introduce the subject, the mechanics of it. Part two will be the orbital mechanics, the flight of the object in space and the track over the ground. Part three, which will be a more extended portion of our radar signature analysis program, will be several tapes on more advanced techniques. And we save the advanced techniques for Part 3 because an understanding of orbital mechanics is required for many of these advanced techniques. So let's just label Part 3 right now, Advanced Techniques. One of the principal reasons for the course on radar signature analysis is not necessarily to just create or train many signature analysts. A desire of ours is to instill in the minds of the radar operator and radar associated people a greater understanding of the radar system. And of course, a much greater understanding can be achieved by understanding the radar equation, what radar cross-section is, and how various targets behave in space, and how their behavior or motions or dynamics affect the tracking ability, the tracking accuracy, and whether or not you can even track some targets. So hopefully this course would be of interest to anybody associated with the radar business, to give you a greater insight into the radar system, tracking problems, and of course problems associated with targets and their dynamics. Now with that introduction, I'd like to encourage you or invite you now to turn to page 1 of your student handout book. I have a copy here I'd like to show you. You can't hardly read that, but it's labeled Radar Signature Analysis Videotape Program Part 1, DAS 107. That stands for a Signature Analysis Course, VT Videotape 1. And in this book, on page 1, you'll find the content principally of tape 1. For example, on page 1 it lists tape 1 lasting 25 minutes in length, and its title is The Introduction to the Program. There's a page or several pages in this book for each tape. There's room for notes, which I encourage you to take as we go through here, and on each page will be a very brief summary of the content of each tape. Furthermore, on each page here will be generally a list of summary equations or the mathematics that were involved in each tape, that you might have these equations handy for your reference. Now there's some mathematics is involved in radar signature analysis. Now generally, the mathematics involved is no more than what a good high school algebra course would cover, and a course on trigonometry. Now we may get a little more advanced as time goes on, but hopefully as we go through the course, each new procedure and technique will be developed to your understanding, that you might understand it. So as you notice on page 1, the introduction to the program, you find Part 1 lists first the introduction, of which this tape is it, and following this introduction, which will be in tape number 2, we'll begin an analysis or a study of that classical equation which is known as the radar equation or the radar range equation. The radar range equation is no more than a group of numbers or factors of the radar system which define radar's performance. It defines the signal-to-noise ratio, which would appear at the output of the radar receiver as a function of such things as target size, the radar transmitted power, antenna gain, the wavelength of the radar, and such things as the noise factor, noise figure of the radar receiver, range to the target, other losses, and so on. So the radar equation will very carefully and methodically develop, that you might understand each factor in it, and from that radar equation we'll then factor out that term known as radar cross-section. And from the term radar cross-section, which appears in the radar equation, we'll then develop just exactly what is radar cross-section. We will define it. We will mathematically define it using a sphere approach, developing the radar cross-section from an investigation of a sphere and how a sphere behaves to a radar. And then from once we've defined and understood what radar cross-section is, and let me define it very simply now as being the apparent size of a radar target to a particular radar system, we'll then relate radar cross-section to various shapes. For example, we'll first investigate the sphere from which we'll derive radar cross-section, Then we'll advance to the cylindrical shape and find out just exactly what the radar cross-section of a cylinder is as a function of the viewing angle. And of course, we'll find that the radar cross-section pattern, oftentimes referred to as the backscatter pattern, is unique for a cylinder. And because of its uniqueness, that is, the variations of cross-section as a function of time, we'll be able to identify a cylinder out in space merely from its cross-section pattern. From the cylinder, we will advance on to and discuss the cone, another common shape. We will consider the flat plate type of target or surface, and then combinations and variations of these, which would include, in the case of a long extended cylinder of very thin diameter, such things as antennas and protrusions. Find out how they behave. Now, we may then, once becoming familiar with the radar cross-section pattern of the various shapes, combine various shapes to find out their composite effect, and then how we might analyze the target from complex patterns. So complex shapes would be the next subject, and toward the end of this portion, part 1 of our signature course, we will consider target dynamics. Now, when I say target dynamics, I mean whatever motions the target may be going through in space, and how it would affect radar cross-section or backscatter pattern, and how we might identify some of these anomalies or distortions to our pattern to be able to relate them to the particular motion of the target. Various target dynamics or motions include such things as spin, precession, tumble, and a particularly useful type of motion which I sort of like to call synchronous tumble, which is, when I say synchronous tumble, I mean the tumble rate of the body is equivalent to its orbital period, where we have what's known as a stable body. A body that's stable in reference to some point on the Earth, whether it's the center of the Earth or the horizon as it appears ahead of the target in its flight path. We have Earth center stability, horizon stability, or any type of stability in between. And of course, stable body would also include a spinning body, a body which has spin energy, acts like a gyroscope in space. Its axis is inertially oriented or inertially stable, and of course we'll study all these. So that would be part 1. Part 2 would go on into the study of orbital mechanics, and most all targets in our Earth orbit, virtually all targets in fact in Earth orbit, are basically elliptic in shape. And we will discuss in length the mathematics of the ellipse. We'll draw it, graph it, construct it, consider it from many aspects, and then we'll place the ellipse of that orbit about the Earth, consider it in relation to its orientation to the Earth and its location, and then we'll set the whole system, Earth and the orbit plane, in the celestial sphere, and find out how it all ties into the celestial sphere. And one of the means by which the mechanics or the parameters of a particular target's orbit are identified or labeled, you might say, is by what is known as an element set. And the most easily understood is that which is called a NORAD element set, or just a element set. It's a group of numbers which identify the various parameters of the orbit. You might refer to them as a NORCAL or as a GP-TP and what have you. Then we'll consider the element sets, each entry in the element set form, what each one is, relate it to the orbit, and how we might use it very briefly. We'll consider the interrange vectors, that is an EFG, an Earth-fixed coordinate system, and the IRVs. Consider those. We'll actually plot a few on the board, or at least one, manually work it out, find a target's position in space as a function of the 3 coordinates in which it's given. Then we'll advance on into re-entry, which I've mentioned earlier, the effects and phenomena of re-entry, how they affect radar. Part 3 of the course, advanced techniques. We'll continue on in the more sophisticated advanced techniques of identifying the things that we can find out about the target. Now, we've talked a lot about what the course will contain. I think it'd be a good point or time at this point to back up and identify what is radar signature analysis. We've talked about it, but we've not identified it. Radar signature analysis, in its broadest meaning, is merely finding out most all you can about a particular target from the data available at a particular radar station. Now, most of our analysis, our course, will be oriented around the single station solution, the single station concept. That is, one radar located on the surface of the Earth, tracking a target as it passes within its radar range, and from the data gathered, analyzing and finding out all that can be obtained about that particular target. A radar signature analysis does include the positional aspect of the target. That is the metric data. That is the point in space where the target is and its motion. Now, we've sometimes limited radar signature analysis to just a pattern analysis. But we must include everything we possibly can about the target. The positional data, its orbital information, and its amplitude variations versus time, and relate these to target motions. So in broadest sense, radar signature analysis includes most everything that can be possibly determined about a target from a particular radar station. Most of the emphasis in this course, at least initially in the first part of the course, will be on analyzing amplitude variations as a function of time to determine size, shape, and motion of the target. Now, I have recently found a model I'd like to show you. This model is the Soviet Vostok space system that put the first man in orbit. This model is very characteristic of many Earth satellites that we'll be seeing, you'll be seeing at your radar station as we throughout the course. We have some radar amplitude recordings from various radar systems that we'll be analyzing, and we do happen to have a radar amplitude recording of this particular satellite configuration, or one probably that's very similar to it. Now, this is the Soviet Vostok. It put Gagarin into orbit, the first man into orbit, and several others. This particular configuration and similar configurations we'll find are in use today. I say this is very characteristic or typical of targets that we'll be analyzing. We're going to find out that this system right here, which contains a upper stage, which portion right here where my hand is, and the payload portion up here. Now, this particular satellite, when it goes into orbit, leaves in orbit two objects. The first object left in orbit, of course, is a payload, and the second one would be a spent rocket casing or rocket body. Every satellite in Earth orbit has associated with it a rocket body or rocket motor of some type that put it in orbit. And in this particular case, this would be the rocket body or motor. You can see one nozzle, one engine on the back. It's basically cylindrical in shape. That put this more complex shape into orbit. Now, what would happen would be when this rocket motor stopped firing, at that point, we have orbit injection. At that point, this satellite and this rocket body are in orbit. And from that point on, the two would separate, the payload would go its way, and the tank would, of course, come along with it. Now, early after a new launch, oftentimes we will see the satellite is given a little initial velocity when it separates from the tank, and it would shoot on out ahead. Because of that, the orbit of the payload would be a little higher than the orbit of the rocket body. And because of that, you'll find the period of the rocket body's orbit will be less, and it will go around the Earth quicker than will the payload. So oftentimes during new launches of most anybody's launch from any site, we'll oftentimes find when we first acquire a target that we'll find the tank out ahead of the payload. And the reason being is in a lower orbit, which has a lower period. And it will, after separation, be in the lower, slightly lower orbit, run on ahead of the rocket body. Now, this rocket body is characteristic of many that we'll be seeing and analyzing some actual records on. This particular rocket body is basically a cylinder. And, of course, the cylinder is one of the shapes we'll begin to analyze and study. This cylinder has, though, a slight conic surface on the base, a truncated cone. A truncated cone is a cone with the top lopped off. It has two flat ends and a conic shape. So you can see a slight cone right here on the edge, if you could see that, a conic surface. Then there's a concave surface, and again another conic surface, which is the rocket nozzle. And the radar will see these various surfaces and produce amplitude variations which we'll be able to identify. So here's a typical rocket body, and I might say this very rocket body we will find in orbit today, an exact, of which this is an exact replica. Maybe, of course, slight variations in length as the shroud portion of the rocket body is changed for different payloads, but basically the same rocket body. Now, we said we would consider the sphere. Many spheres are found in orbit, but unfortunately they're not perfect spheres. For example, this sphere is probably a perfect sphere as far as its basic shape is concerned, but you can see it's got attachments on it. It's got 4 little, what we call hairpin or paperclip antennas up here. In this particular case, it was a command control system. And it's got some long boom-type protrusions, which are low-frequency antennas, sticking out the front of this thing. And these things actually act like long, thin cylinders. So we have a sphere, we have long, thin cylinders or protrusions, and you'll notice on the base a double conic system. Truncated cone here, and a truncated cone here, which the radar would see as the aspect angle or viewing angle would change. We're going to spend some time with this particular satellite. It's not an unusual sight in space, and it's very characteristic of many we may see, so we'll spend some time with this. And as you can see, this is a combination of several shapes that we'll be analyzing. Now, as we go on, toward the end, we may begin to look at some more complex shapes. Now, this happens to be Pioneer 18 satellite. It's difficult to see. It's got a ball, which is an experiment on top of a boom. It's got 4 little wire protrusions sticking up. You can see them flashing here. It's got a base, which is a 8-sided. It's sort of like a very short cylinder, but the cylinder sides are 8 flat surfaces. And it normally being rotating somewhat, flat surfaces will appear. Also, large flat surfaces appear as the solar paddles. A big solar paddle sticking out at the bottom here. These things appear very characteristic to a radar return. And we'll, as we advance, begin to study the effects of more complex shapes such as this. I think that's probably an adequate introduction to our course. We have just a couple minutes left. I'd like to give you some numbers that you might mark down on page 1 in your book. We'll be dealing with such things as wavelengths and frequencies and so on, and we'll be dealing with circles and spheres. And I'd like to give you some numbers, some conversion numbers, and some terms we'll be interested in. If you just might jot them down now, we'll be using them a little later on in the course. So as we step over to the blackboard here, let me put some numbers on the board, and you might just jot these down. First of all, let me tabulate a little table of frequency, wavelength in meters, wavelength in feet, and let's put a label here, band. And we'll begin with some various radar frequencies that you'll be possibly familiar with. First of all, a VHF frequency, which is 185 megahertz. All these will be in megahertz, by the way. 185 megahertz. We find the wavelength of that particular frequency is 1.622 meters and about 5.32 feet. The next one we'll be interested in would be UHF with a frequency, we'll say 425 megahertz, 0.705 meter wavelength, 2.3 feet. Then we have L band, about 1275 megahertz, with a wavelength in meters of decimal 235 and in feet decimal 77. Next would be S band, and we'll just choose a nominal frequency of 3,000 megahertz. The wavelength is decimal 1 meter, which is decimal 328 feet. And C band, we have more than one radar in the C band range, so let me put down about 2 frequencies. 5295 is one frequency that's in use. Another frequency is near 5,600 megahertz. I'm sorry I got these in the wrong column here. Both C-band, 52, 95, and 5,600. The wavelength in meters for these two is 0.056 and 0.054, and the wavelength in feet would be 0.186 and decimal 177. You might jot these down if you don't have them already. Do it very quickly. We'll have to erase it and move on. These are some numbers that will be of use throughout the course. The wavelength in meters and the wavelength in feet at these various frequencies. Now, let's go on over here to the upper right portion of our board. Let me give you some numbers, some conversion numbers. It might be of help. 1 foot equals decimal 3048 meters. Then we have 1 yard equals decimal 9144 meters. We have 1 meter is equal to 3.281 feet. 1 kilometer is equal to decimal 5399 nautical miles. 1 kilometer is equal to 1093.6 yards. Now, those are some handy numbers. Just mark them down right now. We'll be getting to them after a while in later tapes, but we will be using quite often throughout the course the metric system. Well, many of the radar systems measure range in either nautical miles or yards or kiloyards. So there's some conversion numbers for you to mark down. Now, while you look at that for a minute, I'll erase the other part of the board. One more thought, we'll conclude. We'll be using a radian measurement for angles. Now, if you recall, circle is broken up into 360 degrees. That's one convenient way of breaking the circle. If the length of a radius of a circle is inscribed about the arc, circumference of a circle, where the arc length is equal to the radius, the angle inscribed here is equal to 1 radian. 1 radian. And that's equal to about 57.3 degrees. Now, I mention that because there's an equation we'll use throughout this course where it says length is equal to wavelength over 2 delta, where delta is an angle that may be expressed in either radian or degrees. Now, to get radians, all we need to do is divide any angle. Radians is equal to any angle divided by 57.3. Now, the radian method of measuring angles, as far as we're concerned, is almost identical to the sine of an angle. Most of our angles we'll be dealing with are under 20 degrees, and where the radian measurement of, let's say, 20 degrees is about decimal 349. That's 20 degrees expressed in radians, and you'll notice the sine of 20 degrees is about decimal 342. And we see there we have less than decimal 0.7% error. So we'll be using these things interchangeably. My time's run out, so let me conclude now. And I hope you got those numbers. We gave them to you very quick. But with that, we'll like to, I think, probably conclude the introduction to radar signature analysis, and trust you'll be right back in tape number 2 and follow along with us in the radar equation development. RCA radar signature analysis course. We introduced the lesson in tape 1. I think in tape 1 you probably got a good cross-section of the type of information we'll be covering. And we'll not waste any more time now introducing our subject. We've got quite a bit to go through. It'll take several tapes, so I think right now the best thing to do is jump right in with both feet, right in the middle of it. And I believe the best place to start is with the tool we'll be using for data gathering. And of course our tool is the radar system. Now before we can really understand radar signature analysis, we must understand the tool. We just have to know what that radar is, how it works, what it does, and what factors or parameters affect the data, the information we get out of the radar that we'll use for radar signature analysis. So probably the best way to start would be to consider the radar very simply as a transmitter, a receiver, and an antenna. A device that will couple our transmitted energy out into space, and a same device which will receive it back in, apply it to our receiver, and where we might amplify it and use it, put it on some type of recording device. So, over to the blackboard here just for a minute. Let's begin very quickly by considering first our transmitter. Let's just put the transmitter out in space. Consider this dot here, point out in space, and let that point represent the radar transmitter. Now we don't have an antenna yet, we just have a transmitter. And we'll assume that this transmitter just puts energy out in every direction all at once. It puts out energy every direction. It's an isotropic radiator. So to introduce our radar system, let's begin right at the beginning. Let's begin with the transmitted energy. Here it is. This represents the point from which our radar signal emanates. Now, we have to label this something, so normally power is labeled P. In our case, we'll call transmitted power P sub T, the power with the subscript T for transmit. Now, our initial assumption here is a very valid assumption. However, we'll have to modify it when we consider the effect of the radar antenna. Our initial assumption is that this radar antenna, or radar system from the transmitter, is putting out this amount of power, and here we consider peak power in watts. Peak power in watts being transmitted by our antenna, by our radar. And we say it transmits out every direction. Every direction. Isotropic radiator transmits in every direction equally. Now, of course, we know that's not true, but we'll consider it the effects the antenna has in a moment. Considering then that our transmitter being out in free space, radiating in all directions, this the total power being transmitted at any instant of time, of course, when the transmitter is turned on, we can see then that that thing is sort of filling up a sphere when it transmits. It just fills up and expands out into a sphere shape. And if we consider that three-dimensional, we say the transmitter is radiating all directions equally. All directions equally. Well, that's a good place to start with our radar equation. That's a good place to start with the equation that relates all the radar parameters, at least those that affect the signal that's received at the output. Now, the radar equation we're developing, purpose for our development of the radar equation is to consider all the factors that affect the signal-to-noise ratio we get at the output of our radar receiver. So what we're striving for as we develop this equation, bear in mind, is the signal-to-noise ratio available as the output of the radar receiver, or available at the recording device, whether it be in the form of a function record in the AGC level, or a peak video, detected video put on a video recorder and later brought off for analysis work, whatever it might be. The radar equation defines the amount of power being transmitted, and we'll assume initially it's being transmitted in all directions equally. And our goal is to define the signal-to-noise ratio at the output of the radar receiver. After we send a signal out to the target, bounces off the target, comes back, gathered up by the antenna, through the receiver, and out. And of course, during the process of doing all this, some noise is introduced in the loop in the system. So we're striving after signal-to-noise ratio at the output of the receiver. Now, transmitter transmits this amount of power. The first thing we need to consider now is, what about a target? How far away is a target? What are we going to do with that transmitted power? Well, much of it that goes out into space never comes back, but a little bit does. And that little bit that does is what we're interested in. So let's move over here a little bit to the right. And let's put a target out here. Let's put a little target out here at some distance r from the radar. Some distance r. That's the range to the target from the radar antenna. The range to the target from the radar antenna. Now, what? Well, let's find out first how much power is getting over to the target. How much power from this transmitter that we have is getting over to the target. And to understand, to find out how much power is getting over to the target, one of the first things we need to do is to determine exactly what is the power density at the target range. That is, our transmitter is putting out this many watts in all directions uniformly, and this energy is expanding out into an ever-increasing sphere, a surface of a sphere. You might consider it a sphere that's constantly enlarging in size. And the power is evenly distributed over the surface area of that sphere. We need to find out just how much power is in one particular little area of that sphere, let's say in the vicinity of the target. So what do we have? We have a sphere with this being the center, the radius of the sphere being the range to the target. Now, if you recall from your geometry days in high school, the surface area of a sphere. What is the surface area of the sphere? I think you'll recall the surface area of a sphere is equal to 4 times pi times the radius of the sphere squared. Now, that being the surface area of the sphere, we know over any particular sphere, and we'll use the one of radius r, or range r, range to the target, with this range, this amount of power being transmitted out, we can say that at this range, we have this much power uniformly distributed over the surface area of that sphere. The surface area being 4 pi times the range squared. Now, I might say at this point, to be consistent throughout this course, I believe it'd be a good idea if we treat range in meters. Now, the reason for that is later when we begin to consider the effective area or size of the target, the area and size of the target is normally expressed in square meters. And it's very convenient if we use all dimensions in the same system. So let's use range in the metric system, the meters, and they'll give you a conversion factor for yards to meters, nautical miles to meters, and feet to meters a little later on. But right now, let's just consider all distances, all range in meters. Now, surface area, all areas also, by the way, will be in square meters. So, here's our situation. We have this much power being distributed uniformly over a sphere of radius r. Well, let me ask you this question. How might we find out how many watts of this energy is in a surface area, let's say of 1 square meter on the surface area of that sphere? On the surface of the sphere, how many watts are falling in the area of 1 square meter? That's about 39 inches by 39 inches. How many watts are in that one unit area? And that, by the way, is known as power density. Power density, the power over some area. So what's the power density in the vicinity of our radar target? Well, we know that we have this much power on the surface of that sphere. We know this is the number of square meters on the surface of the sphere. So all we need to do is divide the transmitted power by the surface area of the sphere, and that will give us the number of watts in 1 unit area, or 1 square meter, on the surface of the sphere. Now, that's quite simple, so let's do that. Let me erase this and move it out of the way a little bit. Remember now, signal to noise is what we're striving after. So, power density in the vicinity of the target, considering an isotropic radiator, that is a transmitter that transmits equally in all directions, the power density at the surface area of that sphere is equal to the power transmitted divided by the surface area of the sphere, which is 4 pi times the radius of the sphere squared. That will now give us power density at the vicinity of the target. Power density at the vicinity of the target. Well, that was simple. And we're halfway there. We've got the power of the signal from here out to the target. Now the next thing to consider is to forget all about the power of the transmitter. Well, no, let's back up a minute. Let's modify this first of all. Let's remember now that our initial assumption was that the transmitter transmits equally in all directions. Now that's a false assumption. It's a valid assumption for purposes of development of our idea, but it's a false assumption. We know our transmitter doesn't transmit equally in all directions. The transmitter is connected to an antenna, and the antenna has gain. The antenna has gain in the direction of radiation. So what we'll need to do is consider that gain. We'll put an antenna here. And remember that the transmitter is still transmitting P sub t, but the antenna has modified this by a gain factor, G, the transmitting antenna gain. And I better put a little t here to indicate transmitting antenna gain. Now, being familiar with what's known as a reciprocity theorem, I will discuss this probably in 2 or 3 tapes from now when we advance and develop antenna theory. We know that the transmitting antenna gain is the same as a receiving antenna gain. At least we'll use that assumption. Now, let me just label it separately here, transmitting antenna gain. What does gain do? What does gain do? Well, one of the definitions of gain is how much does the signal over here at the target increase by using this antenna compared against how much signal was here initially using the isotropic antenna. And that's one definition of gain. That is, how much does putting this antenna here increase the signal here over what we initially had? That's gain. So gain then affects the power density in the vicinity of the target by what? Well, by the factor of gain. So I can modify this equation now to define target power density at the target vicinity by being just multiplying it by the gain. Power transmitted times the gain of the transmitting antenna in the direction of the target, and now divided by the surface area of the sphere, results and yields the power density. How many watts per 1 square meter of surface area in the vicinity of the target? Now, that's quite simple. Next logical step then is, now that we have some power over here, we're sort of divorced from this thing for the moment, and now we're over here. We have to say now that that target is out there being impinged upon by radiation, by RF energy. What about that energy? Some of it's going to come back. How much is going to come back? How can we figure that out? Well, we need to make another assumption, and this is a valid assumption because by definition, now when you make anything by definition, you can make anything just about be anything. So it's valid. In this case then, we're going to define the effective area of that target by using as a reference a target that doesn't send all the energy back to the receiver, but it causes the energy that strikes that target to be radiated equally or reflected equally in all directions. Well, that's the type of target we'll use, and that's a valid assumption by virtue of the definition of a term that we'll introduce now called radar cross-section. Radar cross-section is most often defined or shown by the little Greek letter, lowercase Greek letter sigma. Lowercase Greek letter sigma. That little sigma represents the effective cross-sectional area of the target, and it's usually given in square meters, and that's why we'll use the range in meters. The effective area of that target is defined as the radar cross-section, and the little Greek letter sigma is used to define or to illustrate sigma, cross-section in square meters. Now, the point I'm trying to do here is, the point I'm trying to come up to is, how much power is actually being picked up by that target? How do we know that? We've already decided from our system here of transmitting this much power with an antenna with this gain, G sub t, and illuminating the surface of a sphere of radius r, at least that portion of the surface in the vicinity of the target. We said now there's this many watts within 1 square meter on the surface of that sphere in the direction of the target. We said this equation right here is an equation that expresses that power density. Power density. So let me label this right here. We'll just call that power density. And we'll call that at target. Power density at target. Power transmitted times the gain of the antenna in the direction of the target divided by 4 times pi times the radius of the sphere squared, which is the surface area of the sphere. Now, how much power, again the question, is intercepted by the target? How many watts? Well, let's say this. If this were, let's give a number, suppose this were 1 watt per square meter. Suppose this term, with these values plugged in, would yield 1 watt per square meter. Now, by the way, power density is always watts per unit area. In this case, watts per square meter. If this equation yield 1 watt per square meter, and the target area, sigma, were 1 square meter, how much power would the target pick up? Well, it'd be the area of the target, 1 square meter, times the power density. And in our illustration, we said 1 watt per square meter. The target would pick up a power of 1 watt. 1 watt. So, very simply then, multiplying, let me remove the target out of here, be a little clearer. Power density at the vicinity of the target times the area of the target, sigma. Power density times sigma would yield now the number of watts intercepted by the target. So the whole term now, this being, well, let's just call that the area of the target. The two together result in the number of watts picked up by the target. The number of watts actually intercepted by that target. Now, where does that leave us? We now have another transmitter over here, what it amounts to. We have a second transmitter sitting out in space, this distance away from the receiving antenna. So let's move over here and consider this transmitter now. This transmitter is putting out this many watts. And by definition, we now have, honestly, an isotropic radiator. That is a transmitting antenna that transmits equally in all directions around that sphere. Now this is valid by definition of radar cross-section, which we'll develop in a later tape. This is our situation then. This many watts, right here, being transmitted by this transmitter. So, let's just reverse the process we did a while ago. Going out into space, we considered this the point source, and the target being over here. Let's back this whole situation up. Turn it all around. And let's suppose now that we have this transmitter, this now being the distance back to the, well, it is the distance to the antenna. We now have a second sphere problem. This is the center of the sphere, this is the radius of the sphere, here's the surface of the sphere. We back this problem up, do just the same thing but in the other direction. This many watts transmitted over that distance, illuminating this area or the surface area of a sphere. Now what's the radius of the sphere? Same as the radius of the sphere going out. What's the surface area of the sphere? It's exactly the same as any sphere. It's 4 times pi times the radius squared. And in our case, we see we're dealing with spheres of the same dimension, both of them having a radius of r. So this being the case, what need we do to this equation to determine how many watts per square meter is falling on the antenna? What's the power density back in the vicinity of the receiving antenna? Power density in the area of the target was merely the transmitted power divided by the surface area of the sphere. and in our case multiplied by the gain of the antenna. Power intercepted by the target was that power density times the area of the target. This becomes then the power transmitted by the target, considering no skin or surface losses or other losses in the antenna or the target. This is the power transmitted now. Before, all we needed to do was divide the power transmitted by the surface area of the sphere. Let's do that again. Power transmitted is this term. And to divide, we can multiply by a number's reciprocal. So we divide this by surface area of the sphere. We get 1 over 4 pi times radius squared. That gives us then power density back in the vicinity of the receiving antenna. Power density in the vicinity of the receiving antenna. And now we're back to the same situation we were at the antenna, or at the target. We had power density in the vicinity of target, multiplied power density by the cross-sectional area of the target, or effective collecting area of the target. We'll do the same thing over here. This is the power density at the vicinity of the receiving antenna. We need to divide that, or multiply the power density by the area of the receiving antenna. And what is the area of the receiving antenna? Well, if you recall from your basic radar days, the classical gain equation for a radar antenna, or any antenna, the classical equation for the gain of an antenna, and I'll develop this in a later tape, so just accept this for the moment. We'll spend some considerable time describing antennas probably in the following tape. If you recall, the gain of an antenna is equal to 4 pi times the aperture, or area of the antenna, divided by the wavelength squared of the frequency the antenna is being used at. Now, the area of the antenna is the area seen looking into the face of the dish. Whatever type dish, generally for radar, parabolic shape. If you look straight into the front of that dish, you'd see a flat disk. Well, that flat disk area is is not the effective area, but it's just called the antenna area. The true or effective area of the dish has to be modified by a factor less than 1, usually in the vicinity of 0.65, due to what's known as illumination taper. Illumination taper. Now, as we develop antenna theory later on, we'll find out that the antenna surface is not uniformly illuminated. And as it's not uniformly illuminated, we find out that the effective area is actually compressed slightly by some factor, anywhere from 0.65 up to 0.95 for some of the best Cassegrainian type systems. So a little factor has to be introduced in here to modify the true area of the antenna to compensate for illumination taper. And that factor is the little Greek letter rho. We'll call it radiation efficiency or aperture efficiency, several terms used to define it. But the point I'm trying to drive at is that the true area of the antenna multiplied by the aperture efficiency factor, or factor determined by illumination taper, actually is the effective area of the antenna. It corresponds to sigma for a target. I better indicate that. Sigma for this target is represented by the factor area times the radiation efficiency. So these two terms multiplied together are the effective area of the antenna. Now what we're after is finding the effective area of the antenna that we might multiply it by the power density at the vicinity of the antenna to determine exactly how many watts of RF energy are being picked up by the antenna itself. So, rearranging this equation a little bit, we'll find out then that antenna area, let me just erase it, I'm running out of room here. The area of the antenna, and let's put a little E here to indicate effective antenna area or antenna aperture. Effective area is equal to radar antenna gain times the wavelength squared divided by 4 pi. Now that was just rearranging our initial equation there for antenna gain. Still have gain, wavelength squared, 4 pi. A sub E represents the true area multiplied by its radiation efficiency or illumination taper efficiency, whatever you want to call it. So, this representing antenna area. What we want to do is multiply the power density, which are these three terms multiplied together, power density in the vicinity of the antenna, by the area of the antenna, the same as we did going out to the target. And we will have then the signal in watts actually intercepted by the radar antenna. So let's do that. Multiplying gain, and this represents, by the way, receiving antenna gain, times the wavelength squared divided by 4 pi, and the whole expression now, let me clean it up a little bit here. The whole expression here now gives the signal in watts actually picked up by the radar receiving antenna. And we see it is a product of the power transmitted times the transmitting antenna gain divided by the surface area of the sphere of radius range to the target times the cross-sectional area of the target. Turn the whole situation around. This becomes the transmitted power now divided by the surface area of a sphere of radius r again. Get power density back at the receiving antenna times the effective area of the receiving antenna. And that results now in a number of watts actually received by the radar receiving antenna. We're not done yet though. We've got a few more terms to go. So hang on here, sharpen your pencil and get some more paper out. We can't do anything with the signal sitting at the antenna terminals. You can't see it, you can't feel it, you can't hear it, you can't do anything with it. It's there, but it's so small, it's not available. So we have to bring it downstairs into the antenna, or into the receiving system. And getting it through the receiving system is quite a problem. I've got some losses to take care of as we go from the antenna down to the receiver. I have noise that's picked up, the inherent thermal noise at the input of any receiving system. And then we have to multiply or consider the noise factor of the radar system. That is, how does the radar handle the noise and the signal? And get it to the output of the receiving system. So let's carry it on. Let's just keep going here and see what we can come up with. This results now, this equation, in the actual antenna power, watts, being picked up by the receiving antenna with this geometry. This transmitter power, this antenna gain, this range, this radar cross-section, so on, or into the receiving system. And getting it through the receiving system is quite a problem. I've got some losses to take care of as we go from the antenna down to the receiver. I have noise that's picked up, the inherent thermal noise at the input of any receiving system. And then we have to multiply or consider the noise factor of the radar system. That is, how does the radar handle the noise and the signal? And get it to the output of the receiving system. So let's carry it on. Let's just keep going here and see what we can come up with. This results now, this equation, in the actual antenna power, watts, being picked up by the receiving antenna with this geometry. This transmitter power, this antenna gain, this range, this radar cross-section, so on. And with this particular antenna aperture. That gets us to the receiving antenna terminals. Let's get downstairs into the receiver now. First thing, let's go from the antenna down to the receiver input. We'll just go from the antenna back to the receiver. We go from here to here. The only thing that happens to the signal is it's attenuated. It's losses in the line. We have to account for the losses. So let's take a term in here that accounts for the losses. We'll multiply it by, well, let's say 1 over some loss factor. Whatever the losses are in the line from here to here, the signal at the antenna these four terms, reduced by the loss from the antenna to the receiver, L. So now we have the receiver down at the input, or the signal at the input to the receiver. Well, that's not the only thing we have there. The signal's not the only thing present at the input to a receiver. There's also noise. We've got to take care of the noise. So what do? Well, normally noise is expressed by a signal-to-noise ratio. That's how we treat the signal from here on. So let's do that. Let's just divide both sides of this equation by noise. Now, if you divide both sides of an equality by the same thing, it remains an equality. If I divide both sides of this equation by noise, it still remains an equality and a valid expression. So what is noise? Well, again, take my word for it at the moment. We'll develop it in a later tape. Let me say that available thermal noise at the input of the radar receiver, at this point, noise is equal to a constant, which is called Boltzmann's constant, times the absolute temperature, and to standardize this we'll use a reference temperature, T sub 0, times bandwidth, which we'll call noise bandwidth. Noise bandwidth. So let me just say this right now, and you might just copy it and get familiar with it. I'll expand on this and show you why this is the noise power available as we progress through these tapes. Noise at the input is defined as the total available thermal noise. It is equal to Boltzmann's constant times the absolute temperature in degrees Kelvin, and here we'll introduce a factor 290 degrees Kelvin. We'll call that a reference. So, dividing this by noise, we have signal to noise at the receiver input terminals is equal to all this mess. K, T sub O, B sub N. Now, that takes us all the way up to the input to the receiver and now accounts for the noise. One more factor to introduce here, and we'll get our signal at the output of the receiver. Now, the receiver does three things. The receiver does three things. It amplifies the signal, it amplifies the noise, and it adds a little extra noise. We have to compensate for that little extra noise, and not compensate for it, but we at least have to account for it. So let's account for it this way. Let's say that we have a term up here called noise figure. Noise figure. Now, if the receiver didn't add any noise whatsoever, it would amplify the signal and the noise in equal amount. If that were the case, the signal-to-noise ratio would not change as it went through the receiver. But it does change. The receiver does add a little bit of noise, which we call delta N. And because it adds a little noise to the bottom part, the signal-to-noise ratio actually gets smaller. Worse, it degrades as it goes through the receiver. So how do we account for that? Well, the noise figure is a number greater than 1, which defines the degradation of the signal-to-noise ratio as it travels through the receiver. So all we need to do is divide our whole expression by noise figure. And I'll put the vinculum over the NF to indicate that noise figure are not two separate terms, but the two together are one term. So we have then the classical radar equation. Now perhaps you don't recognize it in this form. It's rather spread out. Let's see if we can't combine some terms here, and then we'll summarize and conclude our first lesson. Signal-to-noise ratio at the output of the receiver, where we can use it, is equal to, well, we have transmitter power, antenna gain. Now you'll notice antenna gain, we have a transmitting antenna gain here, receiving antenna gain here. Take my word for it again for the moment, they're identical. If we have gain times gain, we have gain squared. Well, what else is up on the top? We have wavelength squared. That came out of the formula or equation for effective area of the antenna. So gain squared times wavelength squared. One more term in the numerator, sigma. Of course, the larger the target, the larger the signal we're going to get. That's pretty clear. Now, what's in the bottom? I think you'll find this will clear up a little bit here. We have 4 pi times 4 pi times 4 pi. So we have plenty of pi's here. We have 4 pi cubed. We have range squared. Range squared results in range to the 4th power. And what else? We go on down here. That takes care of all the pi's and r's. Loss, Boltzmann's constant, K T sub O B sub n, the noise at the input to the receiver, and noise figure. How much does the signal-to-noise ratio degrade as it goes through the receiver? This, then, is the classical radar equation. The classical radar equation. And we find it in all good radar books. Now, unfortunately, most radar books don't develop the radar equation to show you how we get here. Now, this is very important that you understand each factor and each term in this equation. We'll look at this equation, we'll tear it apart, develop it again. We'll develop it from an entirely different aspect. We'll use solid angles instead of the sphere technique we've used. And we're going to become very familiar with the radar range equation. And for the moment, though, I'd like to ask you, if you didn't catch all this, play the tape again. Now, you'll find this is necessary. Some of these cases, it's necessary to play these tapes over and over, perhaps until you get it clear. A solid understanding of the radar equation is an absolute must before we can proceed in radar signature analysis. We'll find out exactly what range, how range affects signal-to-noise ratio at the output of the radar. We'll find out how the power transmitted does it, how much the gain of the antenna affects signal, how much the frequency affects it, how about noise figure, what effect does that have on our tracking ability of the radar, and how large the targets we might see, and what about target size. Now, we need to understand all these because a little later on we'll rearrange this equation and we'll solve this for sigma. Sigma is what we're after. Sigma is an expression or a term which defines the effective cross-sectional area of the radar target. That's our interest, is to find out what is the effective area of the target. And watching then the area variations as a function of time, we'll be able to analyze the size, the shape, and the dynamics of the various targets. So this will be a good point to stop, I think, and let me put a card over here on our card table, and we'll review very quickly this. If we might go to the board here. We find our radar equation then, simplified and expanded. Now, I might leave this here just for a moment if you'd like to copy it down and look at it in detail. We find then that the radar equation defines the signal-to-noise ratio appearing at the receiver output. It is equal to the first term being power density at the target. Power transmitted times antenna gain times divided by the surface area of the sphere of radius r, range to the target. So power density at the target times cross-sectional area of the target sigma. Treat these two terms now as a transmitter power. Divide by the surface area of a sphere of radius r, results in the power density back at the receiving antenna. Receiving antenna area multiplied by power density. The first four terms now become power intercepted by the radar receiver. Now let me move the card over a little bit here. We see the last term modifies and compensates for the losses from the antenna down to the receiver, times the noise figure, times the, of course all this divided by noise figure times the noise at the input to the receiver. This then is the classical radar range equation. Get to know it. It's one of your greatest tools. And I think with that we'll conclude our tape number 2. And I do encourage you, get some paper, a pencil, and get familiar with this equation. In your own time, you might go through and develop what we've done on the board here. Get it clear. It's got to be clear in your mind. And as soon as we get this well understood, we'll advance on this. Now, mathematics looks very complex here. It's not. It's extremely simple. We'll simplify this down very simple here as we advance on. In fact, we'll find out that most every term in the radar equation will be replaced by one number, a number called the radar station constant. And we'll define that constant, find out how to get it. We'll discuss a little later on how you might track a standard target. In this case, a 6-inch sphere. You might suspend that from a balloon, track that thing out to some known range, record the signal level coming off that sphere, and from that information be able to decide and put a value in for most all of the factors and terms we saw in our radar equation. Now, later on, as we understand that radar constant for a known size target of known shape, known cross-section, we'll then be able to analyze the information we have and come up with a shape, for example, of a particular re-entering warhead. Maybe a blunt nose, hemispherical capped cone, or maybe a nose fairing floating around in orbit, or again maybe a re-entering warhead. We'll be able to analyze from our radar return the cross-section that we determined from the radar equation, and as we watch cross-section vary as a function of time, we'll be able to analyze the shape, size, and dynamics or motions of this particular target. And of course, as we go on, we'll advance more complex shapes. Here we have a hemispherical capped cone capping a cylinder with a truncated cone, another truncated cone with a different half angle, and a hemispherical base. We'll be able to analyze every shape and dimension of that target once we understand this radar equation and get a good understanding of our radar system and the information coming out of it. And I think with that we'll close tape number 2, and I might ask you to study this a little bit. We'll continue on in tape number 3. In this lesson, lesson 3 of radar signature analysis, we'd like to expand a little bit on the radar equation. I think we've had a pretty thorough introduction into it in lesson 2, and with a little review and homework, I think probably should be pretty clear right now. What I'd like to do in this tape, in this session, is to expand a little bit on a few of the terms and factors of the radar equation, and see if we can't come up with a little better understanding of some of these factors. Well, one thing that's most important that we understand is the operation of the radar antenna. Not so much the radar antenna itself necessarily, but antennas in general. And we'll find out that contrary to, well, let's say the common belief, the target is not just a bouncer. It's not just a device that bounces a signal back. To truly analyze, at least especially more complex targets, and of course to even understand radar cross-section as we develop it from using just a simple sphere, we'll use a sphere as a standardized target in our development of radar cross-section. We'll find out that the understanding of antenna, and especially the gain and area expression for an antenna, is very, very important. Very important. All targets act as antennas. All targets act as transmitting antennas. They intercept a certain amount of energy. RF currents will flow on the surface of that antenna, or that target, and result in energy being radiated back to the target. For example, this sphere, the one I hold in my hand here, an RF energy will come along and strike that sphere. RF currents will flow over the surface of that sphere, and every single point on the surface of that sphere acts like a point source radiator, a point source transmitting antenna. And all the energy will be re-radiated from this antenna, of course, not considering at this point any losses. There's I squared R losses. Current flows through a resistor. There's heat generated. A surface heat is lost energy. But considering perfect antennas, or perfect reflectors, if you may, we'll say that all the energy that strikes the dish, or the antenna, the sphere, the target, whatever we have, will be re-radiated. But we have to understand how this thing acts as an antenna. it's necessary to be able to derive that term that we've mentioned and introduced on the first tape, or tape number 2, radar cross-section. Radar cross-section being the effective backscattering area, or the effective intercepting area, or the effective cross-sectional area of the target. And we just need to understand antennas. Now, we began, of course, with the radar antenna, and as we went to the radar antenna, the radar equation on the blackboard on the past tape, we found out that as we considered the antenna part of it, the antenna had a gain that was equal to 4 pi times the area of the antenna times a term which we call the radiation efficiency. That may not be the correct name for it. I'll call it radiation efficiency or reflector efficiency. All that stuff divided by the wavelength of the radar squared. And that's the classical gain equation for the antenna. Let's consider, though, where does that equation come from? Where did we get that equation? It just didn't fall out of the sky. Let me erase this for a minute. Let's consider an isotropic antenna. Let's consider an antenna that we'll never have, we'll never see, but it's convenient to consider, so we'll consider it. Let's consider an antenna that is an isotropic antenna, the one we started out with our transmitter and the radar equation, an antenna that radiates equally in all directions. Antenna that radiates equally in all directions. Now let's say that it radiates out here, all directions. It radiates equally in all directions of a sphere. Now, of course, I'm drawing this on a two-dimensional blackboard, but consider it in all dimensions, spherically, radiating out. Now, let's just leave that type of antenna here, and let me move over here now and put another antenna, transmitting antenna. Let's let this antenna just kind of send a signal over toward our isotropic antenna. We found out from the radar equation, as we developed it, that one thing we needed to do to find out how much power is being picked up by this particular antenna or this target was to find out what the power density was here at this antenna. Power density. If this transmitting antenna is putting out a certain number of watts, that energy, let's just say expanding out, results in, over at the vicinity of the target, or in this case, our isotropic antenna, we find out that we needed to multiply the power transmitted by the gain of this antenna in the direction of interest and divide all that by the surface area of the sphere of radius r. In this case, our sphere being centered at the transmitting antenna, and the surface or the radius of the sphere, and the surface of the sphere lying through our isotropic antenna. Now let me label that just for a moment. We'll call that the isotropic antenna. Now you'll see what I'm driving at in a minute. This may seem confusing at the moment, but I think you'll see in a minute. Now what I'm trying to do is define antenna gain. So let's start off this way, with some antenna over here transmitting energy in the direction of our unknown. Well, it's not unknown. Let's just say the isotropic antenna. And we know that the first thing that needs to be done to find out what signal is picked up by this antenna is to find out what the power density at this antenna is. Power density was transmitted power divided by the surface area of the sphere at the distance of the target, or in this case our reference antenna, and multiplied by the gain of the transmitting antenna in the direction of the target. Now, let's erase all this and say that over here, falling at the target is so much power density. Let's just say 1 watt per square meter. That's the power density falling in this little 1 meter square here, impinging on the antenna. How much power is picked up by this antenna? Well, to find out how much power is picked up by this antenna, we need to know what is the effective collecting area of that antenna. Now remember, this little square is moving in this direction. And as it crosses our antenna just sort of captures part of it. It reaches out and cuts off part of it, and part of it comes in the antenna system. So what we need to know is the area of this antenna. Now let me say this just to begin, and perhaps we'll expand on it a little bit later. The area of the isotropic antenna, and just by this for now, is equal to wavelength squared of the antenna divided by 4 pi. That's the area of the isotropic antenna. The effective area of the isotropic antenna being wavelength of the frequency that it's being used at, of course it's cut for it and all that, divided by 4 pi. Now just by that, that's the effective area of the isotropic antenna. Now, we say that that antenna has a gain of 1. We'll just call it 1. We'll say that's our perfect reference antenna. That's an antenna that we don't really have, and I don't believe we could really generate it, but for illustration purposes and for convenience, we'll define and say this antenna is an antenna that radiates equally all directions when it's excited or being used as a transmitting antenna, and as a receiving antenna, it receives equally in all directions. It's non-directional, completely non-directional. Now, I've defined the area of this little isotropic antenna by this equation. Wavelength squared divided by 4 pi. That is the effective collecting area. Now, what would happen if we took that antenna away but kept the same power density here and replaced that with an antenna that had gain, a high gain antenna? We know from our initial conditions that power density, the watts per square meter, times the area of, in this case, our isotropic antenna, would determine how much power was intercepted by the isotropic antenna. Let me place the isotropic back here just for a moment. This area of that antenna times that power density would result in the number of watts picked up by the isotropic antenna. Now, if I would put another antenna here that had gain and measure the number of watts picked up by that antenna, the ratio of those two power levels would be the gain of this antenna by definition. That is, the signal picked up by this antenna, now let's just call it the watts received divided by the watts received for the isotropic antenna. The watts received by this antenna divided by the number of watts that were received for the isotropic antenna is equal to gain. Okay? Now, let's just take that off there. Leave that in your mind there for a moment. The signal picked up by this antenna divided by the signal picked up by the isotropic antenna is gain. Recall this being the area of the isotropic antenna. Let me just move that up out of the way for a minute. The area of the isotropic is equal to wavelength squared over 4 pi. We'll just leave that there for a moment. That, which is area, times power density, I'll just call it PD. Area times power density is equal to watts received. Now, that applies for any antenna. Power density at the antenna by its area is equal to the watts received. Now, we said the watts received for this antenna divided by the watts received for the isotropic antenna. We'll just call this our antenna. How's that? Watts received by our antenna divided by the watts received by the isotropic antenna for the same power density 1 watt per square meter for our illustration, is equal to antenna gain. So, let's do that then. We can replace watts picked up by our antenna by the equation for it. It's the area of our antenna times power density. The watts picked up by the isotropic antenna was the area of the isotropic antenna times power density. Of course, power density in the numerator and denominator, we can just get rid of that, divide it out, and we find out then that gain is equal to the area of our antenna divided by the area of the isotropic antenna. So what are we saying? Well, let's do this. What is the area of this antenna? What is the area of that antenna? Well, if we could take this antenna, bring it down and just turn it around and look face into it. You see a flat dish, a flat circle. That's the area of our antenna. Now in a moment we'll find out that the total area is not really available. The reason it isn't because we don't uniformly illuminate the entire surface of the antenna. We'll find out that the illumination or the RF energy striking the center of the antenna from the transmitter, from the feed assembly, is more than it is out on the edge. In normal cases, the edge is minus 10 dB. This gives us optimum gain versus side lobe energy content. So we find out that the true area, the effective collecting area of this antenna is a little bit less because of this edge taper, because of the illumination of the dish. We'll find out that the factor that reduces the effective or the true area to the effective area is what I'll call for now, it may be a wrong term, radiation efficiency or antenna aperture efficiency. It's a little Greek letter rho. So the area of our antenna times the little Greek letter rho. For standard parabolic antennas, it's normally in the vicinity of 0.65. For super high quality Cassegrainian antennas, it might get as high as 0.95 or maybe even higher. Usually not, but let's say it could get as high as 90-95% efficient. So this area, the frontal area of this dish, times its radiation efficiency is the area of our antenna. And we defined gain as being what? Area of our antenna divided by the area of the isotropic antenna. What's the area of our antenna? It's A times rho. What's the area of the isotropic antenna? We have it up here in the corner of the board. We have wavelength squared over 4 pi being the area of the isotropic antenna. So our antenna area divided by the area of the isotropic antenna, which is wavelength squared over 4 pi, is a gain of any antenna, at least of the radar type. Now, I have a fraction in the denominator. I can multiply numerator and denominator by 4 pi, and we get four pi times the area of the antenna times radiation efficiency, the classical radar gain equation. Now, I want you to remember this very carefully, very thoroughly. We'll be using this equation considerably in development of radar cross-sectional areas of various targets. For example, the sphere. We're going to consider this as an antenna. And as an antenna, we will apply this gain equation. We will find out exactly how much power is picked up by this antenna as the RF energy strikes it. Secondly, we'll just take a little slice off the front edge of this sphere, and we'll look at a little disc on it, and we'll consider that little disc as an antenna that radiates back. And to find out the gain of this little antenna, we'll need to know the gain equation. So we'll apply this antenna equation for gain to a sphere. And we'll come up with the cross-sectional area of this sphere. Secondly, we'll apply that to a cone. We'll just take a little slice off the edge of this cone. We'll consider that edge as an antenna, and we'll derive, using the antenna gain equation, the cross-sectional area of this little cone. And we'll not do that for more complex shapes. In this case, it's hemisphere-capped truncated cone. But I think you'll find it gets very interesting. You'll have a much clearer understanding of what radar cross-section is if you have a good understanding of antenna gain. So remember, gain equation is very simple. It's the area of the antenna of interest divided by the area of an isotropic antenna. That's all it is. It's the ratio of the two areas. This being the area of the isotropic antenna, this being the A times rho, the area of the antenna of interest. Now normally, for targets, not considering antennas now, but for a particular target out in space, maybe a cylinder or a sphere, the two we'll spend most of our time with, we'll not consider the term rho. We won't consider the term rho, we'll consider just the area. We'll take a slice out of it and compute the area of that slice that we've looked at or taken off and use that area. Now the losses in the target which would really affect us would be surface losses, skin losses. What's the skin of the target? Is it painted with a radar absorbent material or is it not? Is it polished aluminum or maybe it's some rough jagged something? Does it have sharp edges and discontinuities? These will all affect it. We'll consider all these to some detail later. But what I'm driving at now is, get this clear in your mind. We'll have to understand radar antenna gain. Now, of course, from the gain equation, we can easily rearrange this. If perhaps we know antenna gain, we can turn this equation around and find out what the effective area of an antenna is. You want to know what the effective area of your antenna is? Rearrange this equation. Let's bring this, let's call these two terms the effective area of the antenna. Take rho out, multiply the two together and call it A sub E. That's the effective area. How do we solve for effective area? What is effective area equal to? Well, let's multiply both sides of this equation by wavelength squared. And what do we get? We get wavelength squared times gain here. And if I multiply this by wavelength squared, it just comes out of the bottom. Now, if I divide both sides of this equation by 4 pi, and divide this by 4 pi, of course that comes out. What's left? A sub E. Effective area of any antenna is equal to the wavelength squared times the antenna gain divided by 4 pi. You know your gain? Maybe your gain is 30 dB. I'll use a easy value here. Your gain is 30 dB. Put in 30 dB. Now what's 30 dB? You don't want to, if you don't want to deal with decibels here, 30 dB is equivalent to 1,000, I believe. Put the value 1,000 in here. Four pi, what's that? Well, it's about, let's say, 12.6, roughly. Wavelength squared, suppose, well, whatever frequency your radar is operating at. Maybe it's operating at 1 meter. Well, let's make it simple. Let's use 12.6 meters. Wavelength times antenna gain, converted to a number other than decibels, divided by what was under here? 4 pi. In this case, if your antenna wavelength were in meters, the result would be effective area 1,000 square meters. It's very simple. You can plug your own values in for your system and very simply come up with the effective area of the antenna. Now, that takes care of the antenna term in the radar equation, and let's just get all this off the board for a minute. In developing our radar equation in the last tape, we began with a radar antenna. Let me move it down a little bit here. And we said the radar antenna had gain, and we transmitted so much power, P sub t. The antenna, of course, being connected to a transmitter, this being the transmitted power, and through a duplexer switch and so on, the signal goes out, re-radiated from the target, comes back into the receiver. The radar equation was interested in what is the signal-to-noise ratio at the output of the receiver. Signal-to-noise ratio at the output of the receiver, we said, was equal to, started with what we started with, the transmitter power, power transmitted, times what? Times the gain of the antenna, divided by 4 pi r squared. Now where did we get all that? Well, we went out here and we placed the target out here at some distance r. We said that this transmitter power illuminates uniformly the surface area of the sphere of radius r. To get power density in the area of the target, we divided the power transmitted by the surface area of a sphere, 4 pi r squared. Antenna having gain increases the power density in the direction of the target by the gain factor. So we multiplied it by gain in the numerator of the expression thus developed. Power density then at the target area times cross-sectional area of the target, radar cross-section, sometimes seen as RCS, resulted in now the number of watts picked up by the target. Watts picked up by the target, we then said were re-radiated from here out in all directions. All directions, equally. Some of it coming back here. Let's find out what the power density is back at the receiving antenna. This being the power transmitted by the target, we divide that by the surface area of a sphere, 4 pi r squared again, give the power density back here. Power density divided by the effective collecting area of the antenna, and what was that? We've just developed that on the board. That was wavelength squared times gain divided by 4 pi. Now, let me collect some terms here for a moment. And now that you have this all memorized anyhow from the past tape, let me just collect some terms here and shorten it on the board so we can keep it all on the screen here. Signal to noise was power transmitted times the gain squared times the wavelength squared times radar cross-section divided by 4 pi cubed range to the 4th power times, well, now the time we got here, we had the power at the output of the antenna terminals. To get it down to the receiver, we had to take care of a loss factor. Now, all good mathematicians have a loss factor available somewhere, a fudge factor. If you work things out and plug things in and it doesn't come out right, then you always have a term in here you can plug the extras in to make it balance. Well, we have one right here. Now, strictly speaking, it will account for the loss from here to here. But we can include in that other losses. Bandwidth mismatch, perhaps the transmitted pulse doesn't fit ideally the receiver response function and we get losses. Many things can account for some loss. And let's just throw all of our losses in here. Kind of a lump term. So that takes care of the signal down to the receiver input. At the receiver input, we pick up noise and we express that as a ratio. Signal power to noise power. We said the noise power at the input was K, Boltzmann's constant, times noise temperature of 290 degrees Kelvin, times noise bandwidth. So that gives a signal-to-noise ratio here at the input to the receiver. One other factor, the receiver modifies the noise figure. Signal-to-noise ratio at the input is greater than the signal-to-noise ratio at the output. Noise figure is defined as, I will expand on this in the following tape. Noise figure is defined as the signal to noise ratio at the input over the signal-to-noise ratio at the output. That, by definition, is the noise figure of any receiver. The signal-to-noise ratio at the output is less than the signal-to-noise ratio at the input. The reason for this should be intuitively obvious. We'll develop it on another lesson. The receiver has gain. It will amplify the signal the same amount as the noise. If I would amplify or multiply the numerator and denominator of a factor by the same amount, I have the same ratio. If I would multiply this by gain and this by gain, it would result in signal to noise at the output, except the receiver also adds some noise to the already existing noise at the input, resulting in the noise in the denominator here being proportionally greater than the noise was proportionally in this term, resulting in this number being a smaller number than this number, because this is greater than that, even more so than just the factor of gain. This was multiplied by gain to give the signal at the output. This was multiplied by gain, plus some noise was added to become the noise at the output. That being the case, this number is always greater than 1. Now, that number expressed in decibels, well, the number can never be less than 1. Now, if it is 1, converting 1 to decibels would result in a noise figure of 0 dB. But the number is always greater than 1. So, signal-to-noise ratio at the input is divided by noise figure to become the signal-to-noise ratio at the output. And thus, our classical radar equation. Signal-to-noise ratio at the output is all that. Now, how's of all that some avail to you at the site? What are you going to do with that big equation? Go around and measure all those? Well, no. You don't need to do that. You don't need to measure your antenna gain. How do you do it anyhow? Most of you probably don't know what your antenna gain is really. You have some published figure, and perhaps some figure was measured which was reasonably valid, but you don't really have any assurance of the value that you have as gain is the true gain of your receiving or your antenna. How about the losses? Do you know all the losses in your radar system? Of course not. You know what the noise bandwidth of your receiver is. Well, you may have some published figure, but how valid is it? How good is your receiver aligned? What's your noise figure? I challenge you, if you'll buy 5 noise figure monitors and plug each one into your receiver system, you'll get 5 different noise figure values. So what's your noise figure? Well, you don't really know that for absolute sure either. So how is this equation useful? We've got all these factors, all these terms, and all these numbers. How do we use it? Well, there's a very simple way. We'll find out that just about all of these factors may be replaced by a simple number. And let's consider these one at a time here. Let's say just during any particular mission. Suppose you've got a mission coming up in a couple hours from now. You tweak your radar all up, you get it all polished up, turn the transmitter on, get everything settled out, you know what your transmitter power is, it's established. Everything's going good. You set your frequency to the frequency you'll operate at, and system's all warmed up. You know the noise figure is going to be fairly constant for a while. The available thermal noise temperature at the input is reasonably constant. Let's just see how we can lump some of these together in one value, one constant, and not have to worry about the individual values. Let's start off here. During your 2-hour mission, let me ask you this question. Will your antenna gain vary? No, it shouldn't. Antenna gain should remain constant. How about transmitter power? Will that remain constant? Yes, it should. You shouldn't be tweaking your transmitter power up and down during a mission. You bring it up to level, set it, and that's it. How about your frequency? Well, for skin tracking, you generally won't change your frequency during a mission. If you do, its change is very small, small percentage of your operating frequency. In fact, it's to a level that's insignificant. How about target cross-section? Will that vary during a mission? It most definitely will. In fact, it's the variation of this value which is the basis for most signature analysis results. It's the monitoring and analyzing of the variations in target size, apparent size, as a function of time that results in your ability to identify target shape, motion, size, and other dynamics. 4 pi. Well, pi's a constant already. It better not vary during a mission. So 4 pi doesn't change. Range, it most certainly will change. We can't mess with range. We'll have to leave it in the equation. It will vary during a mission. But now look at over here. The loss factor, the available noise temperature, and the noise figure. These three terms should not vary a sizable amount during any particular mission. So let's do this. Let's say that K is equal to, well, let me do this. K is equal to gain squared times wavelength squared divided by 4 pi cubed times our loss factor, our total available thermal noise, and noise figure. That's K. And we'll call that the station constant. The station constant, or the radar constant. It's a value that will remain constant during a particular mission of your radar. Now, if I let all these terms equal K, or station constant, what would that do to this equation if I plug K in for all these values? Well, it's quite simple. It simplifies this radar equation to a point where it's very easily understood. We now can say that signal-to-noise ratio is equal to K times what? The only other two variables were sigma and range to the 4th power. That now is our radar equation. The signal-to-noise ratio is equal to the radar constant times radar cross-section divided by the range to the target to the 4th power. Now, how do you find a value for K? What is your radar constant? Well, you want to go out and measure the antenna gain, the frequency, the transmitter power level. Do you want to do all these things? Well, you can, but you probably won't come up with a real accurate figure. You just can't measure all the losses. You just don't know exactly what your noise bandwidth is. You don't know what your receiver transfer function is. You don't know many factors to the degree of accuracy necessary to come up with a good value for K. But let's rearrange that equation. Let's just bring K out and find out what it's equal to. What is K equal to? K, in terms of signal-to-noise, cross-section, and range. K is equal to what? Well, it's equal to the signal-to-noise ratio times range to the 4th power divided by radar cross-section. That's just rearranging this, solving this for K. Multiply both sides by r to the 4th, and that brings that over here. Dividing both sides by sigma, it puts it down here. So we then have K is equal to signal-to-noise times range to the 4th over sigma. Well, how about this then? What can we do with it now? We don't know what this is, but what about this? Signal-to-noise ratio is expressed at the output of the receiver. That's what's going on your recording device. You've calibrated your radar a little bit. You have some idea what signal-to-noise ratio is, what it should be, what it represents. The level on a recorder represents X number of dB signal-to-noise. So, this is available at the output of the radar. Most tracking radars should be able to give you a reasonable value for range. You don't know what K is, but you know what this is, and you have it recorded at the output. You have this being recorded and indicated somewhere on a range machine, a range dial somewhere. Well, how about sigma? sigma. Well, you don't know what the cross-section of a target is, do you? Or do you? Suppose you had a big weather balloon and a long string on it. And you attached that string to a ball that was 6 inches in diameter. Exactly 6 inches in diameter. And let's assume also that you have already attended tapes 4 and 5 of this course. If you've already attended tapes 4 and 5 of this course, then you'll know that this particular ball has a radar cross-section equaling what? 2 pi times A, where A is the radius of that sphere. Looking at that sphere, has a 6-inch diameter, would result in a 3-inch radius. You could plug 3 inches in there for radius of the sphere, multiply it by 2 pi, and we'll come up with some value for cross-section for that sphere. And we'll do that. We'll develop the radar cross-sectional area of a sphere very carefully and in great depth, the detail, in one of the following 2 tapes. But if you have a known size target, and we use the sphere because it's an isotropic radiator, it's the perfect target, if it's a perfect sphere, we'll hang that sphere underneath the balloon, we'll send that balloon on its way, and we'll track that target. And as we track that target, we'll measure its signal-to-noise ratio at various range intervals, and knowing the radar cross-section area, we will come up with a chart that will be, it's a semi-log graph paper, that is, it's logarithmically, it's log scale this direction and it's linear scale up here, semi-log paper. And let's put signal-to-noise ratio here in dB, maybe 10, 20, 30, 40, 50, 60. And over here we'll put range, maybe put 1,000 yards here. Well, let's call it meters, whatever you want to use. 1,000, 10,000, 100,000. Now, of course, at a closer range, they'll have a larger signal-to-noise ratio. Now, we would plot the signal-to-noise ratio as a function of range. We will get a curve looking something like this. Signal-to-noise ratio decreases as range goes out. Of course, that's obvious. Now, this plot right here is known as the R to the 4th curve. It's an R to the 4th curve. Now, loop gain is another term I'd like to introduce at this point. We'll not expand on it in detail right now. Loop gain is a term or a number that defines the loop, you might say, sensitivity of your radar system. From the transmitter on out to the target through your antenna, bounce off the target, come back into your receiving antenna, back down into the receiver, out the output of the receiver and onto your recording device. And you know then that for a particular size target, at a particular range, you'll get some particular value of signal-to-noise ratio. Plotting that results in a R to the 4th curve or a loop gain plot. Loop gain plot. Now, loop gain can be expressed several ways. Now, most of you at a particular, let's say, a MIPR site are familiar with the loop gain in one particular term or expression. On another type of system, loop gain might be defined as the signal-to-noise ratio received from a 6-inch sphere at 10,000 yards. So you might come up with a number that says, well, loop gain is 60 dB. Well, what's that mean? It means that on a 6-inch sphere of known cross-section at 10,000 yards range, I receive 60 dB signal-to-noise signal at the output of the radar. That is an expression of loop gain. This very plot that we have over here on the board is another expression of loop gain. It indicates signal-to-noise ratio as a function of range. For various targets, if I have a target of so many square meters, I can move up a certain amount and find out what it's going to be for a target of, let's say, 100 times more square meters in area. So there's several ways of expressing loop gain, and we'll examine them in detail later. But what I'm trying to drive at is that the loop gain is related to radar constant. The radar constant is a number that's higher for the more sensitive radars. The more power, the more antenna gain, the lower noise temperature or noise figure of a radar receiver. All these factors will result in a higher number for K. The higher the K, the more sensitive, you might say, is your radar system. And I want to expand on that at another time, but just wanted to indicate right now that the radar equation may be modified to be usable. By tracking a known size target, in our illustration a 6-inch sphere, we can compute a value for K without having to determine or measure all these separate values. We just track the known target, examine the range and signal-to-noise ratio, put those three values in, and we have K. We have all these lumped up. We have every loss factor in the entire system in loop accounted for without having to measure every waveguide joint, every transition, every elbow, every dent in the waveguide, and so on to get all the losses. We don't have to worry about receiver bandwidth, noise bandwidth, receiver transfer function, what the shape of the transmitter pulse is, and all these factors. It all lumps out very nicely when we measure it with a known size target. So that's how generally radar K is established. Now, we don't always have to track a 6-inch sphere. There's some spheres traveling around in orbit that are easily tracked by some radars, which can be looked upon. There are other targets. There's cylinders up in the sky. There's, for example, there's a perfect cylinder up in the sky, which is a shroud off of one of the Pegasus satellites, which is a very nearly an ideal calibrating source if one would want to examine its peak cross-section and relate it to what we should be getting off a particular cylinder of that size. It can be used as a calibration device. Many devices in orbit today are available of known dimensions which can be used as calibrating sources. So I think with this we'll probably conclude this tape number 3, lesson 3, and just say that the radar equation is a useful tool. We need to understand this form of the radar equation. Signal-to-noise ratio is equal to the station constant, which is related to loop gain times the radar cross-section divided by range to the 4th. Now, of course, what we're driving at is this term here, sigma. That's our ultimate goal, is to be able to pull that out of the radar equation and know exactly what it means. To know how the various radar parameters affect it, how range affects it, noise figure, all these terms. And we want to eventually pull that expression out, or term out, sigma, and say sigma is equal to signal-to-noise ratio, what? Times range to the 4th divided by radar constant. And we want to examine this and know what this means. And knowing this and having this recorded on a recorder, we'll be able to examine that recorder as a function of time and say, well, if I'm tracking this target with this sigma and it's varying this amount per unit time, I have a shape of a cone. And I might say, well, the cone is tumbling end over end. And I might want to say that the axis of that tumbling cone is oriented out here to space to a right ascension of 20 degrees and a declination of plus 30. All this information is available from a knowledge of the radar equation, knowing what sigma is, and then analyzing sigma to determine the target characteristics. And then applying that information, what we see from that, to some of the other information from the radar, like azimuth, elevation, and range. Be able to find out where it is in space, how is it oriented in space, what is it doing in space, and what is its shape and size. All this information is available, and the context of our course and the following tapes will be to analyze that information to find out exactly what each target is, how to define it, all of its characteristics, and report on this information to the proper using agency. And with that, we'll conclude tape number 3. I'd suggest that you spend a little time meditating upon what's been covered so far and prepare yourself for our following lesson, where we'll expand on several of these ideas introduced already. In this lesson, radar signature analysis number 4, tape number 4, we'd like to continue on with the radar equation a little bit, very briefly summarize what we've covered to date to this point in time, and begin now to take a more detailed look at this term called cross-section, which we've spent considerable time on in the past. Now, just one time, and today, I'd like to very carefully develop the term radar cross-section. Now, we'll make a mathematical analysis of a standard reference type target, and just one time now, I'm not going to do this for all types of targets, but for the one classic shape of sphere, I'd like to develop the radar cross-section for the sphere, that you might get a thorough understanding of just what radar cross-section is and how it might be applied to any shape, any size target. And we'll consider most of the topic today using just a sphere. A 6-inch calibration sphere is what I hold in my hand here. It's a 6-inch aluminum sphere, two halves hooked together. It's a type that's hung under a balloon and used as a reference calibration source. We'll consider this 6-inch sphere, but before we go to that particular size, I think we'll just use the sphere in general. Now, briefly, let me go back to the board here and summarize what we've covered in the past 2 or 3 tapes concerning the radar cross-section. Remember, the radar cross-section was the radar equation was an equation that expressed the signal-to-noise ratio that appears at the output of the radar system. Now, wherever this may appear depends upon the radar system in use. It may be in the form of a AGC level on a function recorder. It may be the video amplitude out of on a visicorder, or it may be video on a video tape recorder. Whatever the end result is, signal to noise was the result of the radar equation as we developed it. We found that the signal to noise ratio was equal to transmitter power times the antenna gain squared times the radar wavelength squared times radar cross-section. All that divided by the terms 4 pi cubed times range to the 4th power times a loss factor times the input total input or available input thermal noise, which was K, Boltzmann's constant, times the reference temperature of 290 degrees Kelvin times the noise bandwidth. All of that on the bottom times the noise figure of the radar receiver. Now, we saw the radar equation as put together here on the board. It was rather bulky and awkward to work with. I think we discussed the fact that it's very difficult to measure with any degree of accuracy the absolute, transmitter power is not too hard, but antenna gain, noise figure, noise power, loss factors, all that. We found out it was rather difficult to measure the individual parameters and put them in that we might have a useful equation, at least as far as field work is concerned. This can be done in the laboratory, and it's of course done by the design engineers in designing a radar system. However, for our purposes, we find in field work it's not convenient to measure all these, and of course it's almost impossible to measure with a sufficient degree of accuracy for our needs. So we considered the radar equation a little further. We looked at each factor in this equation that does not vary during a particular mission. We considered the transmitter power, for example, and decided it doesn't change during a particular mission. If it does, it shouldn't be. Something's wrong, probably. Radar antenna gain doesn't change. Radar frequency normally won't change. 4 pi better not change. The range does change. Radar cross-section does change. And we found out that all these loss and noise terms should not change during any particular mission. So we said that we can equate all these terms that do not vary during a particular mission or do not vary appreciably during a mission to a constant. And we said that's the radar constant. And lumping all these together, we find the radar constant is the transmitter power times the gain squared times the wavelength squared. Sigma does vary, so we'll leave it alone. 4 pi cubed times all the loss and noise factors. Loss, input available thermal noise, and noise figure. Treating all these as constants, we find then that the radar equation simplifies down to a rather easy equation that can be very easily handled in the field. And we found that that equation was signal to noise ratio is equal to K, all this stuff lumped together, times sigma over range to the fourth. Sigma, which is radar cross-section, over range to the fourth. And now we have the classical radar range equation expressed in terms that are easily used on site and can be used by any technician who would desire to do so, to come up with some of the understanding of the sensitivity and some of the characteristics of the radar as far as loop gain is concerned. Well, our next problem was, how do we find K? How do we find a value for K that we can put in for a particular radar site, configured in a particular method for a particular mission? How can we find a value for K that we can plug in here that we might solve the radar equation for any of these other terms? Well, we found out that K is easily determined by rearranging this equation, solving for K, and we say K, I think we saw this in the last tape, K was equal to the signal to noise ratio times range to the fourth divided by radar cross-section sigma. That's the value for K. Now all we needed to do is to track a known size target. And when I say a known size target, let me use, for example, a 6-inch sphere. We'll track a sphere or target that has a known cross-section and plug that value of cross-section into this expression. And as we track this target out to particular ranges, we measure the signal-to-noise ratio, put it in, and measure the range factor, or the range value, and put it into this equation and solve this simple expression for radar constant. Now we track that sphere and take several data points, plot these points on a curve, and we'll come up with a value for K. And we'll do that a little bit later on. Before we go any further, though, I made an assumption. I said we put a target out here of known cross-section, sigma. Now, I'd like to spend most of the tape today, the lesson today, describing and introducing this term sigma to you, radar cross-section. It's the lowercase Greek letter S, sigma. And it is used to denote the factor of the expression radar cross-section. A radar cross-section might be defined simply as the effective area of any particular target as seen by a particular radar. And the several factors that enter into that, and we'll see what they are in a moment. Now, fortunately, a sphere is not frequency dependent, at least as long as the radar wavelength is much smaller than the sphere dimensions. If we have a large sphere, a sphere whose dimensions are larger, much larger than the wavelength of the particular radar in use, we find out that the sphere does not demonstrate frequency-dependent characteristics. Now, unfortunately, almost every other target that is tracked exhibits frequency-dependent characteristics. Almost every target. I guess about the only one that doesn't, besides the sphere, is something like an ogive or any doubly curved surface, maybe something like an egg shape. Now, generally, if it's larger than wavelength, it won't exhibit wavelength or frequency-dependent characteristics, but every other target will. Every single curved surface or plane surfaces, sharp edges and so on, exhibit frequency-dependent characteristics. Now, a sphere becomes frequency sensitive when its size it gets smaller and smaller and approaches the radar wavelength dimensions. For example, in the C-band radar, I believe the wavelength is about 2.2 inches roughly. Now, this sphere has a 3-inch radius. And at the C-band frequencies, this sphere begins to exhibit wavelength dependence. Now, I think we'll find, though, that as we get to a larger sphere than 6-inch, then this quality feature goes away. Now, let's just back up a little bit, and let me talk about radar cross-section now. I think we're finished with all this for the moment. And if there's any question on these equations, you might look in the student handout book which accompanies these tapes for tape lesson number 3 and review the equations that were discussed in lesson number 3. We'll have, of course, all these equations are listed in a handout book summarized for each lesson. So you might spend a little time becoming somewhat familiar with these. Now, let's do this. Let's put our equation back on the board, just briefly. We said, well, we're looking for K. Let's find K. Radar constant is equal to signal-to-noise ratio as seen at the output of the receiver, whatever recording medium you're using, signal-to-noise ratio times range to the 4th power over sigma. Now, in the case of a 6-inch sphere, we'll find out in a moment that the cross-section, sigma, for a, let's just put 6-inch sphere here, is equal to 0.018 square meters. Now, how do I get that? Well, in a past lesson we mentioned that the radar cross-section of a sphere, sigma, for any sphere, and here let me introduce the thought that we're assuming a sphere that's somewhat larger than the radar wavelength. Sigma is equal to pi, it's 4 pi times the radius of the sphere squared. I'm sorry, that's not right. Pi r squared. The cross-sectional area of a sphere is equal to pi times the radius of the sphere squared. Now, just looking at a sphere, all you see is a flat disk, if I just write it here on the board. A flat disk. And this is the radius. We know that pi r squared, pi aren't round, pi r squared. And pi r squared is the area of a circle of radius r. Well, that happens to be the radar cross-sectional area of a 6-inch sphere. And this only works for the sphere, but in this case, the sphere's cross-sectional area is equivalent to the flat disk area of the sphere, or the aspect area, as it's sometimes referred to. So, just let me give that definition now. We'll prove it in just a moment. In the case of the 6-inch sphere, then, what need we do to compute 0.018? Let me erase all this, get a little more room. Values in just for kicks. If the 6-inch sphere has a radius of 3 inches, we find then that cross-sectional area is equal to pi times what? 3 squared. Now, we normally express cross-sectional area in meters, square meters. And if we do it this way, we're going to come up with square inches. So let's convert the inches to meters, and we'll come up with this. Pi then is equal, or cross-sectional area is equal to pi, which is 3.14 times 3 inches. And let's convert to centimeters, and we'll convert to meters, times 2.54 centimeters to the inch squared. Now, doing all that, we come up with a cross-sectional area is equal to 182 square centimeters, which is equal to 0.018 4.18 square meters. Centimeter being 1/100th of a meter. And when we square centimeters, we get what? 10,000ths. So if we move this point over 4 places, if the decimal point's there, we'll move it over, excuse me, there should be a 2 there. 4 places, we'll convert from centimeters to square meters. So we find out that the cross-sectional area of a 6-inch sphere is 0.0182 square meters. Now in a few moments, probably later in this tape, we'll convert that to a decibel form, which is most often used to express cross-section. Decibels relative to a square meter. Well, that's the cross-sectional area of a sphere. Now let's just consider that sphere a little more depth. How do we get that? Well, now here we're going to have to use a little bit of antenna theory that we touched on in the past couple tapes. Let's just go through this. I'd like to have you pay very careful attention to this. I might say this is probably about as deep as we're going to get into any mathematical analysis of any aspect of our course here. But it's rather important, I think, because the term radar cross-section is oftentimes misunderstood. Now, it's not intuitively obvious, but sphere is a little bit misleading sometimes concerning radar cross-section. You look at that sphere, you see a particular area. Now, if it wasn't for the highlights of the light, look at that sphere, all you'd see would be a 6-inch flat disk. Now, that's the cross-sectional area of a sphere, but it's rather unique that that's the case. In the case of the sphere, well, let's back up. Let's consider radar. Looking out into space at a target and discuss radar cross-section. This radar looks out into space, and energy goes out, and some of it strikes the target. Of course, some of it doesn't. Now, of that strikes the sphere, which would be the amount in this area right here, the energy that strikes that sphere is reflected or re-radiated back off that sphere in every direction. Now, the sphere is isotropic in that RF energy that strikes maybe this point is re-radiated off in this direction. Energy that comes right along and skins the edge goes right straight back. And this energy, of course, comes off maybe down there. This energy comes back and is collected by the antenna. So we find out the sphere is a true isotropic radiator. The energy that strikes it comes off in every direction, equally. The energy that strikes that sphere comes off equally in every direction. These arrows back here are probably a little misleading. Should be coming off along the edge up here. The RF energy striking that sphere goes off in every direction. So we see then that it's not every portion of the surface of that sphere that puts energy back to our receiving antenna. We might look at it this way. We might say that there's just a little slice off the leading edge of that sphere that actually sends energy back to our radar antenna. And this is how we'll treat the sphere as we develop through the radar cross-section of a sphere. We'll consider a little thin slice right off the leading edge that does act like an antenna. It captures a certain amount of energy from the radar transmitter and re-radiates it back in the direction of the radar antenna. So let's do that. Let's take a sphere, look at it a little larger in size here, and take a little slice off the front edge. Now, let's just put the sphere up here. A sphere has a radius of, we'll use R. Sphere has a radius R. And let's consider now the leading edge of that sphere. Let's say this much. And just for the sake of illustration, let me just slice a piece off here and say that piece is a piece that reflects energy or re-radiates energy back in the direction of the antenna. Now let me just put the antenna over here. We might remember that the antenna is over here looking at the end of the sphere. Now, how big a slice do we take off of here? Well, let me just put a value in. Let's just say that the depth of this little slice, let me mark it up here, depends upon the wavelength of the radar. And let's say that the depth is equal to wavelength of the radar divided by 4 pi. Now, it can be demonstrated why we choose that value, but I'll not take the time at the moment to do that. Maybe as we progress, we'll do that. Let's just say that we go back from the very tip, leading edge of that sphere, back a distance which is equal to the wavelength of the radar divided by 4 pi, and make a slice. Now, the next thing to do is to look at that slice, the front edge of that. You know, if we would take this sphere now and rotate it, that it would face you, we'd see on the front of that sphere a flat disk. And now we can begin to treat the sphere as a true flat disk, at least that portion of it. This part, from here down to here, that's been cut off, and that part that remains is a flat disk antenna. It's a perfect little antenna. And as the energy from the radar comes out, that little flat disk intercepts a certain amount of area or energy. And of course, what we need to know then to decide how much energy that thing intercepts is to know the flat disk area of this little disk that we've chopped off or developed. So let's do that. Let's figure out what the area of this little disk is. And we'll use a little math here. Let's consider a right triangle from the center of the sphere to the surface. Of course, this would have a distance r. And the base of this right triangle from the center of the sphere to this point, what would its distance be? What would its dimension be? Well, let me label these. Let's call this the center O. We'll call this point A, and this point down here B. Now, to determine the area of this little disk on the front edge of the sphere, we have to know the distance AB. AB would be the radius of the little disk. The area is actually the radius squared times pi. So we'll solve and find out what radius squared is. Now, we know that in the case of a right triangle, the base distance or dimension squared plus the height distance squared is equal to the hypotenuse distance squared. Now, let's use that Pythagorean theorem to our advantage here. We know the hypotenuse is equal to r. The distance 0b, which is the base of this right triangle, is what? What's OB equal to? Well, it's simple. It's the radius of the sphere minus the little distance we've gone in, which is wavelength over 4 pi. Wavelength over 4 pi. That's the distance of the base, or length of the base of the right triangle, 0b. Now, what we're after is the distance AB. The distance or height of this right triangle is equal to the radius of the little sphere of the disk on the front edge of that, or the area of the radius of the disk, which we've cut on the front of the sphere. Now, how do we do that? Well, we know that the distance 0a, which is r, so r squared is equal to what? Well, the base squared, which is 0b, squared, plus ab squared. That's Pythagorean's theorem. Hypotenuse is equal to the sum of the base and the height squared. Now, we're after ab squared, this distance right here. So ab squared is equal to the hypotenuse squared, which is the radius of the sphere, minus OB squared. And we have a value for OB. It's r minus, it's the radius of the sphere minus this little piece in here, which we've defined as wavelength over 4 pi. So, let me then put in OB, the r minus lambda over 4 pi in here, and then we'll find out what the radius of that little circle is, that little disk is. AB squared is equal to radius squared minus this thing, r minus wavelength over 4 pi squared. Now, let's square what's in the parentheses here, and we'll go on. And let me erase all this. You have this in your handout book if you'd like to follow along on that anyhow. So let me erase this. We might have a little more room. And let me square this, and we'll move the equation back up here. AB squared, which, by the way, is the radius of the little disk, is equal to r squared, the hypotenuse, minus this term squared. Now, you algebra students, you recall a method called FOIL. That's the method I use. FOIL says if I'm going to multiply these two terms, which is actually, or if I'm going to square that term, it's actually that term multiplied by itself, r minus lambda over 4 pi. I use the FOIL method. I multiply the first terms. R is the first term of each one of those expressions. R times R is R squared. Outer, it says multiply the outer terms now. R and a minus lambda over 4 pi. So I get minus R lambda over 4 pi. Now the inner term, that's what the I stands for. It's minus lambda over 4 pi times R. That's the inner terms. That's the same as the outer terms. So that would actually make this a 2. Let me clean that up a little bit. 2 times the radius times lambda over 4 pi. And the last terms, L, minus lambda over 4 pi times minus lambda over 4 pi. Minus times a minus is a plus. Lambda times lambda is a lambda squared. 4 pi times 4 pi is 16 pi squared. And then the parentheses. Now, you may not be able to see that too well. So let's clean it up a little bit. Move it down. And we'll find out just exactly what this is all about. AB squared is the radius squared of the little disk we're interested in. We're trying to find the area of the little disk. So, AB squared is equal to, well, let's multiply this minus sign through this equation and get these signs all right. We get r squared minus r squared, minus times a minus is a plus, plus, now we have 2 over 4, which is 1 over 2. So let's just divide this by 2, and we get r lambda over 2 pi. And here we have a minus times a plus is a minus, wavelength squared over 16 pi squared. That results in the, well, simplified now. Let's continue on. This is equal to r squared minus r squared, which is what? Nothing. So these two r's come out, and we end up with r lambda over 2 pi minus wavelength squared over 16 pi squared. And that's the radius of the little flat disk that we're interested in. Now, let's do something here that's going to help us out a bit. This still is a little bit bigger term than I'd like to have. So I'm going to do something that's reasonable, that's allowable, as long as we understand what we're doing. We'll erase this term. I'm just going to say we don't need that term. I'm just going to erase it out of there and leave the radius squared equal to radius times lambda. Now that's the radius of the big sphere, times the radar wavelength divided by 2 pi. Now I can erase this term out of here because we made one assumption initially as we began to discuss this sphere, that the dimensions of the sphere are much larger than the wavelength. Much larger than the wavelength. The dimensions of the sphere are larger than the wavelength. Because they are, we will find out that this is the dominant term in this expression. Radius of the sphere, which is larger than the wavelength, times wavelength divided by 2 pi, this term is much larger than this term, which is just a wavelength squared over 16 pi squared. Now I've worked these values out for a 6-inch sphere at C-band. A 6-inch sphere at C-band, this term, r lambda over 2 pi, equals, and let me just mark it up here, for a 6-inch sphere, decimal 0.00115. Now that's the value of that for a 6-inch sphere at C-band frequencies. The value for this term at C-band is equal to decimal 0.000, 4 zeros instead of 3, 1, and then 93. 193. This number for C-band is approximately 1/10 of this number for C-band. So if I would throw this term away, at C-band, I'd only introduce about a 10% error in the equation. Now I mentioned earlier that a 6-inch sphere for C-band frequencies is getting small enough in dimensions where it's becoming wavelength dependent. That is, the cross-section is affected by the radar wavelength. Now, the initial assumption was that the dimensions of the sphere were much larger than the radar wavelength. A 6-inch sphere is not much larger than the radar wavelength when used at C-band. So, I've taken probably one of the worst case examples. We've used a sphere that's very close in dimensions to the radar wavelength. The radar wavelength of C-band is 2.2 inches. The 6-inch sphere radius is only 3 inches. So they're very close in dimensions. Now, this equation that we're using then is valid when we are considering spheres much larger than the radar wavelength. For example, a 12-inch sphere for C-band radar would, the error would be much less than this. It would be about 5%, or actually a little less maybe than 5% error. And as you get larger, the percentage of error drops down to 1%, 0.5%, and smaller error. Now, what we're doing here is saying then, by definition, we're developing the cross-sectional area of a sphere which is much larger than radar wavelength. Now, if that's the case, I can erase this term. And for spheres that are much larger than the radar wavelength, the elimination of that term is almost insignificant, very small. So, let's say then that the radius of that little disk squared, AB squared. Now that's the radius of the little disk squared. I'm not going to take the square root of it because later on when we use it we'll need it squared. So let's just leave it squared right now. Is equal to radius times wavelength divided by 2 pi. That becomes a radius of the little disk, and we've sliced off the nose of this sphere back a depth of wavelength over 4 pi. That is the radius, or the radius squared of that little disk. Now, what's that do? We said that the little disk gathers a certain amount of radar energy. It acts like an antenna. It picks up energy. The aperture or area of that little disk is the area that picks up the energy. So what's the area of that little disk? Let me just write it here. Area is equal to pi times the radius squared. Now, that's the area of a disk, a flat circle. Radius squared of this disk of interest is equal to the radius of the big sphere times wavelength divided by 2 pi. We already have it squared, so let's put it in. Area of that disk then, well, let's leave that there for a moment. Pi r squared. Area of the little disk, looking back towards the radar antenna, is equal to pi times this, r lambda over 2 pi. Pi in the numerator divided by pi in the denominator just cancels. And area is equal to radius of the big sphere, 6-inch or whatever size sphere we're using, the radius of the sphere, times the radar wavelength over 2. And we find then this is the area of the disk. So that's the collecting area of any sphere whose dimensions are greater, much greater than the radar wavelength. Now that's a very important little area right there. I want to use that area to define radar cross-section. I'm going to define radar cross-section, RCS, which is sigma. Better move it down a little bit. I'm going to need some room. Let's move that up here. Area of the disk was equal to, what did we say? Radius times lambda over 2. Radar cross-section, sigma, is equal to the capture area of the sphere, and we've just decided this is the capture area, times the gain of that little area as an antenna. I'm going to say that that little disk is an antenna. I've already said that. And that little antenna picks up so much power, power being determined by one factor being the area of that disk. Radar cross-section then is defined as that area times the gain of that little disk treated as an antenna. Okay, let's go on. You're probably getting weary by now, but follow along. You can stop and let your mind cool off after we get finished here. Refresh yourself and review these expressions as we have them in your handout book. But let's just develop them right now. And let me say then, radar cross-section is equal to area times the gain of that thing as an antenna. The area, radius times wavelength divided by 2. What's the gain of an antenna? Well, we've already had that. Gain is equal to, I think we said, the area of an antenna divided by the effective area of an isotropic antenna at the same wavelength. And we said that was equal to wavelength squared divided by 4 pi. We said the gain of an antenna is equal to then multiplying numerator and denominator by 4 pi. 4 pi times the area over wavelength squared. That's the gain of the antenna. Now, what's the area of this antenna? We've already found that. The area of that antenna is radius times wavelength over 2. The gain of that thing as an antenna is equal to 4 pi times its area divided by wavelength squared. Radar cross-section is equal to the capture area, which is the area, times the gain of that thing as an antenna. Gain being 4 pi times its area over wavelength squared. So let's do that. Cross-section is equal to area, which is radius times lambda over 2, times the gain. The gain of that thing is 4 pi divided by wavelength squared times its area as an antenna, times its area, which is radius times wavelength over 2. That becomes then the cross-sectional area of the sphere. Any sphere whose dimensions are larger than the radar wavelength. Now, we can look at that and very easily solve that. We have cross-section is equal to, we have R times R. What's that? R squared. We have a 4 pi. Let's put that over here. 4 pi times R squared. We have 2 lambdas in the top, so we can put lambda squared. All that's divided by 2 times 2, which is 4, by lambda squared. And the result is 4's cancel, lambdas cancel, sigma is equal to pi times radius squared. Now that's what we started off with. Found out that the cross-sectional area of a sphere is equal to its flat disk area. Now you'll notice throughout the development of this cross-sectional expression a term that consistently popped up, and that was wavelength. Radar wavelength. It popped up here in the area. It popped up here in the radius squared of the disk. It was in the gain equation. But for a sphere, when we got right down to the bottom, we find out wavelengths cancel out. And what's that mean? That means the cross-sectional area of a sphere whose dimensions are larger than the radar wavelength, which was our assumption, is not wavelength dependent. It becomes insensitive to the frequency and becomes dependent entirely upon its physical, optical, or area, or its aspect area. It's independent of the radar frequency. Now, about the only other area, surface, or shape, that's independent of radar wavelength is I think what they call an ogive, or a oval shape, like an egg, any doubly curved surface. Every other surface, every other shape, as we would develop such a cross-section expression for any other shape, for example, this cylinder, the cone, the long rods, wires, antennas, and so on, you will find out that they result in a cross-sectional equation with the wavelength term left in. So almost every other shape is frequency dependent, wavelength dependent. And the effective size depends in part upon the radar frequency. For the sphere, this is not the case. The sphere, whose dimensions are larger than wavelength, is not dependent upon wavelength, and is the very reason why it is an excellent calibration type sphere. It presents a constant cross-section to all radars, to all frequencies, provided that the dimensions of the sphere are larger, much larger than the radar wavelength. Now, an interesting feature happens here as the radar cross-sectional area, or target size, gets smaller and smaller. I'd like to go to the overhead camera now and look at this little curve I'm going to put on a card here. If we could have the... We have a curve here that shows a relationship between, first on the side here, the radar cross-section sigma divided by pi r squared. Now, we're considering a sphere. Consider just a sphere. We find that just in considering the sphere, cross-sectional area here, which is sigma on the top, is the area seen by the radar of a sphere. Its cross-section as seen by the radar. The term in the bottom here, which is pi r squared, is the radar cross-sectional area as it should be, and as it is when the dimensions of the sphere are much larger than the radar wavelength. Now, what am I saying? I'm saying here we're plotting on the ordinate of this graph the cross-section seen, sigma, over the cross-section as we've developed on the blackboard a few minutes ago. That's the ordinate, and you'll see the value 1 right here. 1 meaning this true area, or the area seen, is equivalent to the area it should be. Now, across the abscissa here, we're plotting the radius of the sphere, r, divided by the wavelength of the radar. Now, I've shown for this sphere or for this curve, the 6-inch sphere and the points that a 6-inch sphere would fall on this curve for various radars. Now you can't see it probably too clear, but over right here is the X-band point. That is, for an X-band radar, 6-inch sphere would fall in this portion of the curve. C-band radar would fall right here. S-band radar, which means we're getting longer wavelength, which means the sphere is getting smaller in proportion to the radar wavelength. S-band would fall here, L-band here, and UHF way down here. Now, this curve is interesting. When the wavelength of the sphere of the radar is much less than the dimensions of the sphere, that is, we have a large sphere relative to the wavelength, the curve falls way out here and goes off to the right. Now, and we find out then that the ratio of the measured cross-section to what its physical or optical cross-section is, sigma over pi r squared, is equal to 1. That is, its computed value is equal to its measured value. Now, as the sphere gets smaller and smaller, which means the radius of the sphere divided by wavelength gets smaller, the sphere approaches the wavelength dimensions. We find out that we come out of this area called C, which is known as the physical optics region. And that's the region we've been developing or working in on our blackboard. As the sphere begins to get smaller, it begins to exhibit resonant characteristics, you might say. It begins to resonate. It becomes down to the vicinity of the dimension of the wavelength. And the cross-section then begins to change as a function of frequency. And as the sphere gets smaller and smaller, you can see the variations get greater and larger, until we get down to this point right here. At this point, the measured cross-section for this particular relationship, for this case would be a 6-inch sphere at a frequency just a little bit above UHF. That point, the measured value of radar cross-section is about 5.7 dB above the physical optics cross-sectional area. Now 5.7 dB is very close to 6 dB. 6 dB is a 4-to-1 ratio, which means then at this point, if we had a sphere with this particular size wavelength relationship, the measured value would be about 4 times greater than the true value. And we get down on this point of the curve, we find out that it drops off about minus 4 dB. The measured value would be about 4 dB less than the physical optics region. And we see then that as the wavelength gets large compared to the sphere size, or the sphere comes down to the dimensions of the radar, we have a problem. Now we'll treat this problem in the next lesson. I think this would probably be a good point to close. I'd like to suggest, though, that you spend a little time studying the book that's associated with this lesson. Look in lesson 4 and go over these equations a little bit, and you might even want to work out this problem for a 6-inch sphere, the problem that we have on the board. Work that out for the 6-inch sphere and put the values in, 3 inches for the radius, and convert that thing around to get the square meters, cross-sectional area in square meters of 6-inch sphere at C-band frequencies. I think at C-band we find the wavelength is about 2.2 inches. So I think with that we'll conclude lesson number 4 and continue this thought in lesson number 5. Here in lesson 5, we'd like to continue on with our subject study of radar cross-section. As you recall in the previous tape, lesson 4, we developed the radar cross-section equation for the sphere. And we used the sphere because the sphere has been decided to be used as a standardized type of target, as a reference. Radar cross-section itself, the very definition, is based upon the return of a particular target compared against the return or apparent size of a spherical type target. So a sphere is a good place to start, as we did in describing radar cross-section, developing it, finding out just what it is. And I think to begin this lesson, number 5, we probably should redefine very carefully radar cross-section, at least review very briefly the radar cross-section as we have developed it in the previous tape. And then with these definitions in mind as to what radar cross-section is, we'll continue on into the radar equation, into the simplified form of it, and actually work out a few problems using various size targets and target range and signal-to-noise ratios seen by the radar. So to begin, let's just go over to the blackboard here. We talked about the sphere in the previous tape. We drew a sphere on the board and we considered the little flat disk area. If we could look at this closely here, we decided on the sphere problem that if we would go in a depth of wavelength over 4 pi from the leading edge of the sphere back and consider a little flat disk area there, that we could consider that little flat disk area as being the true area of the sphere as seen by the radar. Now this is fine mathematically and theoretically, but actually in fact this is not the only contributor to energy that would be coming back toward the radar. For example, if we would put the radar here and move it out, the radar we led you to believe in the past tape would see just this area. Well, in essence, effectively it does, but in fact, every single point on this sphere becomes a radiating antenna. And for example, if you'd consider this point down here, if RF energy strikes that point actually sends out energy in all directions, virtually. Of course, most of it would be out in this direction, obeying the normal optical laws of reflection. So actually every point on here is a contributor to the total signal coming back. But for convenience, we have defined the little flat disk area here, which we've solved the size of in the past tape, as being the sole contributor to the energy coming back to the radar. But actually now the whole thing really contributes. Now, in deciding what this little area was and actually calculating on the front of the sphere a little flat disk area, which we said would be the area seen by the radar, we gave a definition of radar cross-section in the past tape as being the area of that little disk on the front edge of the sphere, area of that disk times its gain. Times its gain was cross-section, or sigma. Radar cross-section is equal to the area times its gain as an antenna, the gain of the little flat disk whose area we're considering. Now, if you recall gain of an antenna from our previous tapes, we said gain was equal to 4 pi times the area of an antenna divided by a wavelength squared. So our cross-section became then area of this little disk, which we called the letter A, area times gain. Gain was 4 pi times area over wavelength squared. And area times that would be area squared. So that's radar cross-section of a sphere. Now this general expression right here then, that is the cross-section is equal to its area, which we've computed by slicing a piece off wavelength over 4 pi deep, times the gain of that particular area acting as a flat disk antenna. Now that's a valid expression, and probably the most useful expression for radar cross-section there is for most targets. Now, I'd mentioned in an earlier tape that we'll probably slice a piece off the front of a cylinder and actually work this out. I think I'm going to renege on that and save that for a later tape. Now, as you recall from our introduction, this program is divided into 3 parts. Part 1 is the introduction and basics to signature, which we're in now. It will be comprised of 15 tapes. Part 2 will be the part on orbital mechanics, and Part 3 will be more advanced techniques. I believe in Part 3 we'll take a more detailed look at the actual radar cross-section, at least the mathematics of it, for the various shapes, the more classical shapes being the flat plate, the cone, the cylinder, and the sphere. We've already seen the sphere. We'll probably advance a little bit on the other shapes in the more advanced tape. Right now I'm just trying to establish some basic principles in these first 15 tapes that we can use as a foundation for further studies. Well, back to the board for a minute. This then becomes the general expression or definition of the radar cross-section of any particular target. It's the area, and now this may be the problem. How do you decide what the area will be? Well, in the case of the sphere, we've said wavelength over 4 pi deep. From the leading edge back, take a slice out, compute the area, and that's the area. And we'll examine the other shapes in more detail later. So it's the area times the gain of that particular area as an antenna. And it would result then in A area times the gain equation, and we'd result ultimately in 4 pi times area squared over wavelength squared. And that would be the radar cross-section. Now, the radar cross-section, as seen in this expression, will be in units that were put in this case, for area. Now, if the area was given in square meters and wavelength in meters, this would result in square meters. Area squared. Area is in square meters. So square meters squared would be meters to the 4th power. Wavelength in meters, meters squared would be meters squared, and up here meters to the 4th power. They would cancel. The 2 and the 4 would go into, 2 would go into the 4 twice. So we'd end up with square meters as the dimension. It's very handy oftentimes when you get a little confused in areas like this, what dimensions do they come out in, is to provide or do a dimension analysis. Now in this case, let me just do that one time to illustrate what I'm saying here. A dimension analysis would be, let's rearrange it. Let's put this equation up a little higher. Sigma is equal to 4 pi times area squared over wavelength squared. Now just don't worry about the numbers in here, but just put in the dimensions that will normally be seen. And sigma is equal to, in this case, 4 pi is a constant. It does not have dimensions. It's not measured in feet, inches, pounds, or ergs. It's a dimensionless number. Area is measured in square meters. But we have area squared. Area squared. So in this case, the numerator would have meters squared as area squared. Wavelength is in meters in this example, squared, so we'd have meters squared. And we could, meters squared squared would be meters to the 4th power, and have meters to the 4th power over meters squared equals meters squared. So this is a dimension analysis, or dimensional analysis, and it's useful in deciding exactly what terms or dimensions the result will come out in. The radar equation, I'm going to leave this for a homework practice or example for you, homework problem, but you might take the radar equation that we've developed in the previous tapes and actually stick the dimensions in without putting values in for the factors and see what dimensions this comes out in. It's rather interesting. Well, let's go on. We've now decided that radar cross-section, for our example, for our cases, will be in square meters. Now let's just leave that in the back of our minds for a moment. The definition for radar cross-section is being area times its gain as an antenna, and it will be expressed in square units, and if wavelength and the other terms are put in meters, of course the results will be square meters. If you'd put yards in, the results would be square yards. Whatever you put in will come out in that unit. Now, of course, you might enter with yards and want square meters, so there's a little conversion number between yards and meters that you could multiply by, and we'll probably do that later. Give you the few numbers here to do that with. But just leave this in the back of your mind now, the definition for radar cross-section. Let's back up 2 tapes in our minds and go back to the radar equation. Now let me on the board very quickly put the radar equation as you have seen it in the past. And we said radar equation was equal to signal and noise is equal to power transmitted times antenna gain squared times radar wavelength squared times radar cross-section, all divided by the constant 4 pi cubed range to the 4th power times a loss factor to compensate for waveguide losses and other losses. And then we went into Boltzmann's constant, T sub O, B sub n. Now these three terms being the equivalent noise power, the effective noise power at the input to the receiver terminals. It's the thermal noise that's available at the input. Boltzmann's constant times the reference temperature of 290 degrees Kelvin, or absolute, times the noise bandwidth. Now I might say this, the noise bandwidth is not the same as the system 3 dB or half power bandwidth. The noise bandwidth is a bandwidth that's normalized over the receiver transfer function. It's normalized, and it's a rectangular bandwidth that's mathematically derived. And perhaps in a later tape on noise we'll go through exactly what the difference between noise bandwidth and 3 dB bandwidth. Most radar receivers use what's known as a triple stagger tuned IF strip, which means 9 IF amplifiers. The first 3 would be tuned to 3 different frequencies, the next 3 tuned to the same 3 different frequencies, and then the third group the same way. And with that the case, the noise bandwidth is about 1.01 times the 3 dB bandwidth. So it's very close, but I might caution you at this point, the 3 dB bandwidth is not noise bandwidth. It's very close, but it's not quite the same. Well, anyhow, our radar equation is all these in the numerator over all this in the denominator times, we said, noise figure. And the term noise figure was put in here to modify the signal-to-noise ratio we see at the input to the radar receiver, that it would be modified by whatever the receiver does noise-wise, so that this now becomes the signal-to-noise ratio at the output of the receiver. We know the signal-to-noise ratio at the output is less than that at the input because the receiver amplifies noise the same amount as it amplifies the signal, plus it adds a little more noise in the denominator here. So noise figure is the term to define or describe the degradation of the noise signal-to-noise ratio as it passes through the receiver. Now, that's the classic radar equation. We went a little further last time and simplified it. We had shown that several of these terms are constant during a particular mission. For example, power, antenna gain, and wavelength, 4 pi. And all these terms remain constant during any particular mission or track. And that being the case, we can pull all those terms out and lump them together as a constant and say that the constant is equal to power transmitted times gain squared times wavelength squared times, well, cross-section is a variable. We don't put that in there as a constant. Divided by 4 pi cubed times the loss times Boltzmann's constant, reference temperature, noise bandwidth, and noise figure. That's the constant. Now with all those terms replaced by a constant which we'll call the letter K, then the radar equation simplifies to become signal-to-noise ratio is equal to a constant times sigma. Let me move it up and make it a little more even. Constant times sigma over range to the 4th power. And that's where we left you last time, I believe, with the radar equation. Signal-to-noise ratio at the output of the receiver is equal to the radar constant times the cross-sectional area of the target divided by the range of the target to the 4th power. And of course that came out of the denominator up here. Now let's erase some of this. Now let's kind of put together our knowledge of radar cross-section now along with radar equation. Let me move this up here. Signal-to-noise ratio is equal to constant times sigma over range to the 4th power. Now, what we need to do, first of all, for any particular radar system, in whatever operating mode you'll be operating in, is to decide what K is for that particular radar in this particular configuration. For example, many radars operate at different PRFs. They have different transmitter pulse widths. And to correspond with the transmitter pulse width, the receiver bandwidth needs to be adjusted. We use the matched filter technique oftentimes, where the receiver bandwidth is approximately 1.5 or twice the reciprocal of the pulse width. So the spectrum of the transmitter pulse pretty much matches the bandwidth characteristics of the receiver. And of course, that matched filter theory produces at the output of the radar peak signal to RMS noise. Peak signal to RMS noise. It gives you sort of an optimum signal-to-noise ratio. And we know that as the radar transmitter changes pulse width, receiver bandwidth must change. When receiver bandwidth changes, K changes. Because when the receiver bandwidth changes, the noise bandwidth changes, and K will vary. So a value for K needs to be decided or determined for each radar, for each mode of operation that it has. When I say mode, I say those modes which affect receiver bandwidth. And the pulse, of course, changing transmitter pulse width will affect receiver bandwidth. So if you've decided you're going to operate in a 5 microsecond pulse, or 1 microsecond transmitter pulse width, whatever it is, in that mode of operation, you would find out what K is for your radar at that particular time. Now this can be done, we've mentioned in the past, by tracking a known size target. Looking at the radar equation, there's 3 terms here that are variable. Signal-to-noise ratio, the range, and a radar cross-section. Now if we had some way of putting a known value of cross-section in, it would become a constant. If we could measure range, measure signal-to-noise ratio, we could very easily decide and compute what the radar constant is for that particular configuration and time for that radar. And rearranging this equation, we can find out that K is equal to signal-to-noise ratio times range to the 4th power over sigma. K is equal to all those. Signal-to-noise times range to the 4th power over sigma. And it's not too difficult to come up with a target that's of a particular known size, and we can put the value of sigma in there, track that target by maybe attaching it to a short string under a weather balloon, sending it on its way out into space, measure the range, measure signal-to-noise ratio, put the value of the known size target in, and compute K for that radar. And that's exactly what's done. Normally what's used is the 6-inch calibration sphere. This sphere has known dimensions, has a 3-inch radius, it's 6 inches in diameter, and hung underneath a string and tracked out in space becomes an excellent calibration target. And the problem is now to convert that to, well, let's say square meters. Normally cross-section is measured in square meters. Now let's be consistent and use square meters. And let's find out just exactly how we can come out with K. To do that initially, we need to be able to find out what that is in square meters. Now the 6-inch sphere, as we've already found out in our past tape, has a cross-sectional area of pi times a radius squared. And we know from this particular case that the radius is 3 inches. 3 inches. So sigma is equal to pi, which is 3.14 times radius squared. Now, to convert inches to meters, we need to multiply inches times a factor that will convert it to meters, which is 3 inches times 0.0254. There's 2.54 centimeters per inch. 2.54 centimeters per inch, or 0.0254 meters per inch. So 0.0254 meters per inch times 3 inches squared would be radius squared converted to meters. And then we multiply that by pi, and the result is sigma is equal to 0.0182 square meters. So that's all there is to that. Sigma for a 6-inch sphere, 3-inch radius, is equal to 0.0182 square meters. So that settles the problem of the target size in trying to compute radar constant. Radar constant now is equal to the signal-to-noise ratio times range to the 4th power divided by target cross-sectional area, in this case 0.0182 square meters. Well, that's a good start, but I think we've probably run into a little bit of a problem here already. If you look at signal-to-noise ratio on the output of the radar, in most cases it's expressed in decibels. Range is normally expressed in yards, perhaps meters or nautical miles, feet, whatever dimensions are. And we found out here that cross-sections in square meters. Now we'll need to be consistent in the type of units we're putting in here. For example, we cannot multiply signal-to-noise ratio in decibels times range in yards to the 4th power divided by cross-section in square meters and have anything that means anything. Either we will need to express signal-to-noise ratio in a numerical value other than logarithms and be consistent in our dimensions here, or convert everything to the logarithmic form. And it's very convenient to convert everything to the decibel or logarithmic form before we go ahead and compute or calculate radar constant. The radar equation is much easier solved in the decibel form. So let me give you a very quick refresher here on logarithms and decibels, very brief. And let's convert all these terms into the logarithmic or decibel form and then go on and solve for radar K. Let's first take cross-section. Cross-section. Signal-to-noise, as I've mentioned, is normally already expressed in decibels. So we'll just leave signal-to-noise in decibels as is normally expressed on AGC record. Now, cross-section, sigma, we said was 0.0182 square meters. 0.0182 square meters. How can we convert that to logarithmic form of decibels? If you recall from your basic electronics days, decibels is equal to 10 times the log to the base 10 of a ratio. For example, if an amplifier had a 10 dB gain, what does that mean? It means that we found the log to the base 10 of the power at the output divided by the power at the input, multiplied the log of that ratio by 10, and we had decibels. For example, the ratio of 10 to 1. The ratio of 10 to 1 has a logarithm of 0.2. 10 to 1, right, it'd be 1. Ratio of 1, or the log of 1 is 1, and 10 times that would be 10. So we found out 10 dB is a ratio of 10 to 1. Now we found out, for example, 100. The logarithm of 100 is 2. I'm going to say dB reference to a square meter, or dBSM, which is, before I take the decimal number, let's take a real number. Let's suppose we have a 10 square meter target. A 10 square meter target. That's the target. And to convert that to decibels, what I would need to do is multiply the log times the base 10 of 10 square meters over the ratio over 1 square meter. Now in this example, with the SM here, I'm saying that we will use 1 square meter as the reference. Now you've heard the term dBW, dB watts. That's the ratio of any power to 1 watt of power. dBm, that's the ratio of a power to 1 milliwatt as a reference level. Here we're using a square meter, 1 square meter as a reference level. So to convert 10 square meters to decibels, all that needs to be done is 10 times the log to the base 10 of 10 square meters over 1 square meter. Of course, the square meters cancel. We have 10 to 1, or the result is 10. Now what's the log of 10? The log of 10, we got 10.000. First thing to do is to find the characteristic. Recall the characteristic of any number is equal to 1 less than the number of significant digits left of the decimal point. We have 2 digits left of the decimal point, so the characteristic is 1. The mantissa of 1 is 0. So it's 1.000 would be the log of 10. 10 times 1.000 would come out 10. So in this case, 10 square meters is equal to 10 dB SM. 10 square meters is equal to 10 dB SM. Now what that says is that 10 square meters is 10 dB above 1 square meter. That's all we're saying. So 10 square meters is 10 times or 10 dB above 1 square meter. 10 dB happens to be 10 to 1 ratio. Now let's just put a little chart up here for a moment. And use your memory a little bit from your basic electronics days. Let's put up here square meters and over here dB SM. We've already had a value of 10. 10 square meters, we said, was 10 dB SM. 10 meters squared. How about, well, let me ask you this. What would 2 square meters be? What's 2 square meters? Well, that's a ratio of 2 square meter to 1 square meter, or 2 to 1, converted to decibels. And if you recall, the characteristic of 2 is 0. The mantissa is decimal 3. So it would be decimal 3 times 10 would be 3. If you recall that 3 dB represents a 2 to 1 ratio. So 2 square meters would be equal to 3 dB SM. 1 square meter would be equal to half of this. Now, if I could cut anything by half, I reduce it 3 dB. 3 dB is a 2 to 1 change. So 3 dB from that would be 0. 0 dB SM, which is our reference level, is 1 square meter. How about 4 square meters? That's double this. So I add 3 more dB onto it. It comes out 6 dB SM. 100 square meters. That's a ratio of 100 to 1. That corresponds to 20 dB SM. How about a half a square meter? A half a square meter is 1/2 of this value, or 3 dB removed or down from the 0 dB level. So 1/2 square meter would correspond to minus 3 dB SM. And I think you can see now the relationship between decibels and area in square meters. It's a simple relationship, the same as power is to decibels. And it's extremely handy now. We can convert area, any area, to square meters, of course, and then convert it onto decibel system. It makes it very handy in solving the radar equation. And I'll show you why here. I'll show you why over here. If you recall, our radar equation which said K, in this case we're solving through radar constant, K is equal to the signal-to-noise ratio times range to the fourth power divided by sigma. In the decibel system, we don't multiply decibels. To multiply two numbers, we can merely add the decibel or logarithm equivalent of that number. So in decibels, K in decibels would be equal to the signal-to-noise ratio in dB added to the range to the fourth power in decibels, and we would subtract, to divide using decibels, we subtract the log equivalents. So that would be minus sigma in dB, or dBSM. That's how the radar equation can be worked out in the decibel form. Now, signal-to-noise ratio is generally expressed in decibels. Range is generally expressed in some units, yards, meters, feet, miles, or something. We'll have to convert that to the decibel system. The last one we've just shown, sigma, can be expressed in dBSM. Now for the 6-inch sphere, we found out that sigma is equal to 0.0182 square meters. 0.0182 square meters. And converting that to decibels comes out, I'm not going to go through it right now. Let's just leave that up as an exercise for you. I might say at this point, we have a book called Radar Signature Analysis, DAS 107, which is available as a supplementary study book for this particular course. It's a book that's been around a long time, but in the back of this book, which is available to you, it's not the student handout that goes with this course, it's an additional book that you may obtain. In the back is a little book part on mathematics, basic mathematics, and it goes through logarithms. And I might suggest that you, if you don't have the book, to get it, and to study the part on logarithms, become familiar with them, that you might work these out without any hang-ups. Get familiar with them. 0.0182 square meters is equivalent to minus 17.5 dBSM. And to solve this radar equation for K, we need to have a value for cross-section in dB form, which is minus 17.5 dBSM for the 6-inch sphere. So what we'll do is replace sigma with dBSM, and let's just do it down here, minus the value in dBSM, but the value is a negative value, so it's minus 17.5. Signal-to-noise ratio, let's suppose that we're tracking a 6-inch sphere out to 10,000 meters. And at 10,000 meters, we get a signal-to-noise ratio of 60 dB. So let's put 60 dB in here. Well, we don't need the parentheses. 60 dB plus range to the fourth power. Now, let's quickly go through this and we'll summarize. 60 dB signal-to-noise plus range to the fourth power minus that. And in this case, we said range was 10,000 meters. To convert that to logs, remember now we're going to take range to the fourth power. To convert that to logarithms, we have 10 log to the base 10 of 10,000 to the fourth power. Now to raise that to the fourth power, I could go ahead and multiply that by itself 4 times, raise it to the fourth power, or we have another little trick in logs. This number raised to the fourth power is equivalent to the log of that number times 4. So I can take the 4 from here and move it out here and say 4 times 10, which becomes 40, log to the base 10 of 10,000. Now the characteristic of this, there's 5 digits, so the characteristic's 4, mantissa is 0, we have the value 4. Log to the base 10 of 10,000 is 4. So 10,000 meters to the 4th power, expressed in decibels, will be 4 times 40, or 160 dB, and we could say reference to 1 meter. Now all we need to do is plug that in here, and we have 60 dB signal to noise ratio plus 160, which is 10,000 meters raised to the 4th power expressed in decibels, minus this number. Now minus times a minus is a plus, so that becomes plus 17.5. Adding all these up, we get 60 and 160 is 220, plus 17.5 is 235, 237.5 dB. In this case, I think you'd find it be dB meter. So that's the radar equation then simplified, expressed in decibels using the decibel form. And I'd like to suggest that you actually plug some sample values in here, work it out, get familiar with this radar equation, because you'll be using it in the future. It's extremely important when we start talking about loop gain and radar sensitivity, and actually begin computing some cross-sectional values, especially in the case of a MIP or another system that records the signal level and signal to noise ratio and does not convert to square meters directly. Some radars do convert directly to square meters, some don't. So I think with that we'll probably come to a close of Lesson 5. I trust that this has been a help, and I would like to suggest that you play with some numbers, put some actual values in, get used to this business before we actually continue further. So take a little time study, and with that we'll close Lesson number 5. Welcome to Lesson 6 of our radar signature analysis course. I hope I haven't frightened anybody away so far with a little bit of mathematics we've had. I think today we'll probably begin to get into the more practical aspect once a foundation has been established for the fundamentals of radar cross-section and the radar range equation. Today I'd like to introduce now a little bit the cross-section characteristics of a cylinder. Now we'll find as we go through our course and analyze various targets that most targets are made up of very basic geometric shapes. For example, here we have the cylinder. Quite often the cylinder will be combined with a conic to make some type of vehicle, nose cone, warhead, or rocket body somewhat. And many shapes have spherical surfaces on them, so of course we've already analyzed the sphere to some degree. I think probably today we should introduce the cylinder, which we have here a representation of. The cylinder, look at that cylinder from various aspect angles, find out just exactly what it looks like to the radar as we examine it from different viewpoints. And once become quite familiar with the cylinder, we'll then advance into the more complex shapes. Now a cylinder and a sphere are the two general shapes generally used. Of course, then the conic is added to that as an interstage. Say, for instance, between a warhead or a nose cone and a rocket body. Between two separate sections of a launch system, between the secondary or second stage and the third stage, we might find a truncated conic intersection. So these three shapes, the cylinder, cone, and the conic, will be the shapes we'll dwell on in some depth. Now, we'll not make such a mathematical treatise of these as we have the radar equation and the cross-section for a sphere. I think we've had about enough math for a while, so let's begin with a practical discussion here and begin to consider this target as the radar really sees it. Now, going to the blackboard here, let's briefly establish our conditions. We're considering now, of course, a radar sitting on the ground somewhere, and throughout most of this course we'll be considering airborne targets, either satellites in orbit or some portion of a launch system that's in its suborbital flight. Now, we've already thoroughly examined the sphere, I think. What does a sphere look like to a radar? we found out that no matter how the radar looks at the sphere, it sees the same thing. The sphere rotates, it looks the same. The sphere turns end over end, it always looks the same. No matter how you look at it, the sphere looks the same, provided it's a perfect sphere and it's smooth. So that's why the sphere is used for a calibration source. That's why a sphere is ideal for a reference source for calibrating the radar, because it always looks the same. Now, we can't say the same thing about a cylinder. Cylinder behaves somewhat different. Put a cylinder out here, and we can just about by intuition here see that the radar looking at the side of a cylinder sees a much larger cross-sectional area than, let's say, if the cylinder were rotated, well, let's say 45 degrees away from the normal. Now, in this case, obeying the laws of reflection, we find the RF energy striking the edge of the cylinder most of it would be reflected off in some other direction. So we can see as the cylinder changes its orientation that the effect of its cross-section on the radar is going to vary. And of course, as the cylinder rotates to the point where we're perpendicular to a side, we know then that obeying the normal laws of optical reflection, the RF energy would essentially come right back toward the radar. Much of it would. So that's our cylinder. I think we have a little idea here, perhaps, that we might be able to use this information, this fact that the apparent size of the cylinder varies as the orientation or dynamics of the cylinder vary. And that's exactly how we decide what shape this particular target is by watching its cross-sectional variations as a function of time. And of course, if the target is experiencing any motion at all, as time goes on, it will change its aspect angle or viewing angle as far as the radar sees it is concerned. So this is the secret or the key behind analysis work in at least analyzing the shapes of various targets. Well, let's take our radar down for a minute, and let me draw a cylinder on the board. And let's consider that. If we have a radar system down here somewhere, let's put it down looking straight up at it, and the radar system is sending RF energy out into space, the energy will strike the surface of that cylinder. Now, what happens? Well, it doesn't really just bounce back. What happens is the wave front of RF energy that strikes the surface of that cylinder along the edge causes RF currents to flow all around that cylinder. In fact, every point on that cylinder just about is conducting RF currents. Now, what happens is whenever RF currents flow in any conductor, that conductor becomes an antenna and radiates. So that's exactly what we have in the case of a cylinder. If a radar is transmitting a plane polarized wave or a RF energy in a plane wavefront, when it strikes the front surface of this cylinder, it causes RF currents to flow in every point, and every single point on here becomes a little antenna. Now, when an antenna radiates a single point, it actually radiates in all directions. Now, why would we see a sizable return back in this direction, though, if every little point is actually radiating, well, virtually in every direction? What happens is the phase of the RF currents at each one of these points along the front edge of that cylinder is identical, provided that the radar is looking at the cylinder from an exact 90-degree angle or normal to the surface. If that's the case and all these RF currents flowing or have the same phase, we'll find out then that the RF energy from each point on the surface of this cylinder back in this direction has exactly the same phase angle. And we have constructive interference, which means that all the energy from that point in phase in this direction back toward the antenna, we get a considerable amount of signal radiated down toward the antenna. This is backscatter or re-radiation of the RF energy. Now, this reflection, if you'll allow me to use that word, this energy coming back to the antenna from a perpendicular illumination of the surface is known as a specular return. Specular return. That is a cylinder side specular, or in this case just a cylinder specular. The cylinder specular. Specular meaning the reflection when we're perpendicular from a surface. Now, if we could rotate the cylinder a little bit, well, let's just leave our radar where it is and rotate the cylinder just a little bit. The RF energy now striking this surface will do what? Is it going to come straight back? No, actually it's going to obey the normal optical laws of reflection, which say that the angle of incidence must equal the angle of reflection, which means that the energy coming here will bounce away over here. Now it doesn't really bounce, it's re-radiated, with the most of it being over in this direction. And the reason being is that the RF currents now, again with a plane wave front, striking this surface, we'll find out that the RF currents at different points along the edge of this cylinder are out of phase with each other now. They have a different phase angle, one point to the next. And it just happens that in this direction, all the phases are equal. That is, looking at it in this direction as we travel and we find out that the constructive interference now takes place in this direction. So, looking at the cylinder from an angle here, and let's call that angle theta. It's the angle from the normal or perpendicular of the side of the cylinder. We'll find there is some energy coming back to the radar, but not very much. Most of it is bouncing off over here where the angle of reflection is equal to the angle of incidence. Incidence being theta. So this angle from here over to here, of course, would be 2 theta. Now, we said, though, that this cylinder acts virtually like an antenna. And acting as an antenna, it has the same characteristics of an antenna. I don't think you can find nearly any antenna that doesn't have some side lobe content. And that's the very feature of this cylinder. If we could plot the radiation pattern from the side of the cylinder, if we would put the cylinder back up this way and illuminate this with the radar, again perpendicular to the surface, we would find that the cylinder acting as an antenna would have a primary lobe back in the direction of the radar antenna. And that's the main specular. The main specular. Now, back to our little session we had on antennas a few tapes back. I don't recall if we mentioned that or not. Perhaps not. There was a relationship between the diameter of the parabolic reflector of the antenna and the lobe width that came off or the beam width of the primary pattern from the antenna. For normal parabolic antennas, I believe the lobe width is in the order of, let's say beam width of an antenna is in the order of 70 times wavelength over the diameter of the antenna. If you had a 30-foot dish, at C-band you could put about 2.1 inches in here for wavelength, about 30 feet converted to inches in here, times 70, and you'd have approximately the beam width of the antenna. Now we have about the same relationship with this cylinder. However, instead of dealing with the diameter of the antenna, the dimension we're interested in is the length. The length of the cylinder. Now the length of the cylinder is directly related to both radar wavelength and, I should say the beam width. The angular width of this principal lobe reflected back off the or re-radiated from the antenna effect of the cylinder, the beam width of that is directly related to the wavelength and the length of the cylinder. And we're going to use that information to be able to determine the length of the cylinder as we would track it in space by being able to measure the width of this lobe as it moves through our antenna pattern. Now, this then is the basic information we have to deal with, at least as far as shape analysis, shape determination is concerned. It's probably one of the most principal and one of the best methods available for determining dimensions as well as shape, and that's the beam pattern or the lobe pattern that we see. Now, I said this acts like an antenna. We have a principal lobe and we have side lobes. And in this case, we'll find there will be side lobes coming off the side of this thing. And the side lobes will generally have a width about 1/2 the width of the primary lobe. If I would assign an angular dimension here, whatever the beam width happened to be between null to null, and just say that had a width of 2 delta, delta being some factor, then the width of the secondary lobe, the first 2 or 3 side lobes, would be delta. Delta. So this is one of the principal characteristics of the cylinder. The side lobe width is half that of the principal lobe, or specular lobe width. And that's a pretty handy feature. We find next then that, well, let's examine this first. Let's examine this first. If the radar is at this point illuminating the side of this cylinder, and this is the resultant beam pattern, what's going to happen if I would move the antenna over here, right here, and then look up in this direction? What kind of signal would I see back at the radar? Well, now don't jump to any conclusions here. We've got to consider something. If the radar now, which is the illuminating device, that is, it's the device putting energy on the cylinder, is looking at it from this direction, what will happen to this beam pattern to start with? The backscatter pattern or the antenna radiation pattern from the cylinder. Now, something significant is going to happen here that we have to consider. If the radar would move in this direction, this beam will move over in this direction an equal amount. We have to obey the normal laws of reflection. And if that's the case, it would appear initially that looking in here we would see a null and have very little signal returned back to our radar. But that's not true necessarily. What will happen will be, as the radar moves away from the normal, and normally, of course, this is caused by the target actually in motion, the radar looking now in this direction will result in the main lobe pattern coming off over here, again obeying the normal optical laws of reflection. And then we'd have the side lobes. So in this event, with this illustration, we see we do get a null. That is a very minimum amount of RF signal coming back to the radar antenna. But we have to remember this effect as the angle changes, that is the angle theta, changes from 0 to some other value, the specular moves away from the normal the same amount. Now, this results then in a pattern which we'll call the cross-section pattern or backscatter pattern from the cylinder. Now, in the static case, which is the antenna here looking perpendicular to the surface, we had the standard side lobe coming, or principal lobe, specular, returning right here. And we could look at that thing and then sort of say, well, this is the pattern we're going to get, but the problem is as the radar moves one direction, this pattern moves the same rate in the opposite direction. So the resultant pattern, as seen by the radar as it examines this thing, and we travel all the way around here, are lobes that are actually narrower, lobes that are narrower than what we would see here in the static case. And the resultant pattern would be then, as far as what the radar sees as it views this thing from different aspect angles. And let me define aspect angle right now. We'll be using it. If I would draw a line right through the center of the cylinder and come out the other end, this line is known as the axis of revolution, or the longitudinal axis of the cylinder. Now the angle between the radar line of sight, and this is the radar line of sight, between the radar line of sight and the longitudinal axis is the little Greek letter eta, lowercase e, which is eta. That is the aspect angle. You might become familiar with that term. Eta is the aspect angle. It's the angle that the radar sees the target at as measured from the longitudinal axis, or the axis of symmetry, axis of revolution, spin axis, whatever you want to call it. So that axis, that angle is the aspect angle. The radar line of sight is the line from the radar to the center of the object, and the angle theta, we've already mentioned, is the angle between radar line of sight and the normal, the perpendicular to the cylinder, which is theta. So we have a relationship here. Theta is equal to 90 degrees minus the aspect angle eta. Theta is equal to 90 degrees minus the aspect angle eta. You might just remember that. Now back to our problem here. Because of the fact that the actual radiation pattern away from the side of the cylinder moves in the opposite direction from the radar, as it would appear to look at this from a different angles, we find then that the resultant pattern from the side of the cylinder will be very similar to what it initially was, but with half-width lobes. The lobes are just half as wide as they appeared in the static case. Now, we have here then, very nicely, the backscatter pattern. This is the energy that the radar would see as it looks at the target from different angles. From here, we'd see the maximum. As I move away a little bit, I see a minimum. Move away a little more, then I'd see the next side lobe, and right on around. And actually, as the radar would view that, as that thing tumbled through space, through the radar line of sight, if I recorded the amplitude of all this information on some type of recording device, I could probably see, let's say if that were tumbling through space and the radar observing it, I would probably see, when it was looking at it from the side, a large lobe, and then the side lobes, maybe some other stuff, and finally when it got all the way around to the other side, side lobes would come again, and then the big lobe. So right there, we have perhaps a representative pattern of what the radar might see from this thing as, let's say, for example, the radar stayed here and the target rotated. We'd see one side lobe, go around through the main lobe, through the side lobes, around the end, and then perhaps see the other side. So that's typical. That's very characteristic of a rotating cylinder, or tumbling cylinder anyhow. And well, let's go on. Let's just suppose that we watched this for quite a while. Let me shorten that a little bit so we can get some more room here. Suppose we observed this cylinder for quite some time, and we'd end up with a pattern such as this. What would you do with that? We've got obviously a big signal, big return at this point in time. As time went on, it popped up again. As time went on, it popped up again, and again later. What would we have here? If you were an analyst, with a little bit of information you have already, could you make any sense out of that? Could you make any sense out of that pattern? Well, you'd have to say something's happening over and over again. You could see a pattern here that's similar to that, which is similar to that, which is similar to that, and right on down your recorder, whatever type of recorder you have, recording the return signal strength from the target. Maybe you're recording the AGC level. perhaps automatic gain control level on your function recorder. And you see a high AGC level, then low, then high, then a bunch of low ones. Well, obviously something's happening here with the target, and whatever it is, it appears to be doing it over and over and over and over. Well, this is the repetitive nature of such a phenomenon as we have here, in this case a tumbling cylinder. A cylinder that's rotating end over end. And as the radar looks at these normals or perpendiculars to the side, every time it sees that, it sees a large signal. So you should be able to say from this, very briefly, that the cylinder, it's apparently a cylinder because these are fairly equally spaced out, and only a cylinder actually would provide consistently, evenly spaced specular returns. And you could look at that and use a little imagination and say, well, if this represents the return from one side of the cylinder, let's say that's side A, and this is the next one, that's probably the other side, because it has its own pattern also. So if that's A and that's B, this would probably be back to A again. The time from A to B to A, this time, if I could look on the timing track along the edge of the function recorder, that time along there would represent probably the period of rotation of that cylinder. That's how long it takes to make 360 degrees of rotation. So this is probably one of the simplest type of target shapes and motions to analyze, and that's the tumbling cylinder. Generally speaking, there are special cases now that it gets a little more complex, which we'll look at. But this is probably the most simple and intuitively obvious solution. That something's happening over and over and over again. It's happening very consistently, regularly. Probably this is one side, the other, and then the first side again. If that's the case, the time between here and here, look on the edge of your recorder and get the time difference from this point to this, represents the time that it requires to tumble. It's called the tumble period. If that's 38 seconds in time measured from here to here, that means that that target is rotating slowly. It takes about 38 seconds for it to tumble one complete revolution. Now that's not an unusual number. That's a very common figure, 38 seconds. It's a very reasonable rate for some of the rocket bodies that are accompanying payloads in orbit. By the way, of course, when we get into orbital mechanics, you'll find out that for every single target in orbit, there's a rocket motor somewhere. There's a rocket motor associated with that. Now, it may be attached to the payload, to the satellite, or it may be a separate rocket motor, little solid fuel rocket motor, or perhaps liquid, as some are, that boosted the thing into orbit and then separated, but it went along with it in orbit. So every time you're tracking a satellite, well, at least a newer one, generally you'll find a rocket body either right ahead of it or right behind it. Ahead of it if it's in a lower orbit, and behind it if it's in a higher orbit, probably. Now we'll get into that when we get into orbital mechanics. But right here, if that were the AGC record on your radar from a target that you picked up, let's say associated with a new launch, in all probability you have enough information already from this little bit that we've covered in this course to say that is probably a tumbling cylinder. Now most satellites aren't cylinders. Most satellites are a little more complex shaped than cylinders, but most rocket bodies are basically cylinders, so you could probably say with a reasonable degree of assurance that that's the rocket body in orbit that boosted to some satellite into orbit. And that's a reasonable assessment. And you could furthermore come up and say, well, it has a period of about 38 seconds. That's its rotational period. One rotation, 38 seconds. There's more information you can get out of this, though. Much more. Let's consider size. Let's consider size a little bit. Now let me move the cylinder up so we have a little clearer demonstration here. Let's say this is the signal returned and seen on the AGC record of the radar, and up here we have the cylinder again. And as you recall, I said earlier, a few moments ago, that there's a relationship between the length of a cylinder and the width of the side lobe, or the principal lobe. Now the principal lobe, we said, had a width of 2 delta. 2 delta. Now what? How can we relate that information? We've got the lobes measured and displayed on a recorder, but what we're interested in is finding out what does that lobe or that pulse represent width-wise in degrees. Now this angle, 2 delta, is going to be measured in degrees or radians. So let's stick to degrees. And we need to somehow decide what is the width of that thing in degrees before we can relate it to length. The little equation for length, by the way, the length of the cylinder is equal to the wavelength of the radar divided by the sine of the angle 2 delta. The sine of the angle 2 delta. Now, with that information available, we should be able to come up with the length of this target that we've just tracked. We've tracked it, we've got the amplitude information, we have the width information, the lobe width, but how do we have that lobe width information? What type of form is it in? The function recorder records time along the edge. All recording devices, virtually, record time along some timing track. Now, if I've established that what I've seen here on this recorder is first this side lobe or specular, secondly the one off the other side as this thing rotated and presented its other side to the radar, and then as it continued to rotate back to the first side. What do I have here as far as time and angle is concerned? Well, one complete rotation of the cylinder represents about, well, exactly 360 degrees of rotation of that cylinder. Now, one rotation is also represented by 38 seconds in time. So I should be able to correlate seconds to degrees. If there's 38 seconds in this interval of time, and that time represents 360 degrees of rotation of the cylinder, obviously there's a relationship. And there is. If I would divide 38 seconds by 360 degrees, the result would be the number of degrees in 1 second. I'm sorry, in this case, if I would turn that over, let's do it the other way around. Let's take 360 degrees and divide it by 38 seconds. If we do it that way, that will give us the number of degrees in 1 second of time. And I would be able to go here and step off 1 second interval on the time chart and say, well, that 1 second interval equals that number of degrees. In this case, 38 into 360 probably works out to be about 8.5 or 9 degrees. Let's say 9. Let's say 38 into 360 is approximately 9. So let's say there's 9 degrees then. I better move that up a little bit. That would result in then that the timing across here results in 9 degrees per second. Now, let's go a little further. Suppose I measure the width of that from null to null, from one null to the next. I measure that interval or that space, and I find out that exactly 2 seconds. If that's 2 seconds in time, how wide is the principal lobe from the side of that cylinder in degrees? Well, we said 9 degrees per second. We have 2 seconds, so obviously then 2 delta is equal to 18 degrees. Now, 18 degrees, I can plug that in here for 2 delta, and the length then becomes sine of 18 degrees divided into the wavelength of the radar. Now, let's use UHF band radar just for kicks. I'm familiar with that number off the top of my head. There's not much else there. The length would be then, for UHF radar, the wavelength's about 2.3 feet, divided by the sine of 18 degrees. Now let me look at a little table we have over here. We'll look up the sine of 18 degrees and plug a value in and see what we get. Sine of 18 degrees is decimal 309. Decimal 309. And this, by the way, was 2.3 feet. Now, in this particular case, if we were tracking this with a UHF radar, and these were the lobes we had seen on the AGC record, we could look at that and say then that that represents 360 degrees in 38 seconds. In 1 second, that represents 9 degrees, approximately. The width of the lobe is 2 seconds, so 2 times 9, we said, was 18 degrees. 18 degrees could plug into here. The length of the cylinder, then, is equal to the wavelength of the radar, 2.3 feet, divided by the sine of 18 degrees, which is decimal 309, and we get about 3 into 23 goes about roughly 7 times. So length is approximately 7 feet. Now, 10% accuracy, well, I'll say at 90% accuracy, no more than 10% error is very realistic in lobe width measurements and determining the length of such objects as cylinders, or maybe a side of a cone, or the length of an antenna protrusion. And all this information is available from lobe width. And as I say, getting a dimension here within 10% of its true value is a very realistic achievement. It's done regularly, just from lobe width information. Now, I went through this rather quickly. We're going to spend a little more time on this in subsequent lessons, on actual analysis of these lobes and pulses and nulls and dips and peaks, and relate that to target dynamics, target shape, target motions, target dimensions, and so on. But I wanted to breeze through this one time just to show you what we're driving at, give you a little introduction into it, and first, though, I wanted to show you how we do need to consider the target as an actual antenna with an antenna radiating pattern. Now, it has an unusual pattern. The target is actually a parasitic-driven element. It's like an antenna that has parasitic elements. You have one element that's driven, that has the RF energy going to it. The rest of them actually pick up energy, and RF currents flow in them, and they radiate on their own from then. Well, this is the same thing. The radar antenna is the device that's actually providing the power for this antenna. The radar antenna sends the energy up, it strikes the target, and then RF currents flow on the surfaces of the target, every surface, by the way, and every point on that surface radiates energy back, some in all directions, virtually. And then we find that because of the phase relationships of the RF currents at various points of this antenna, our target, we find when we're perpendicular to this surface, we get a very strong return back. That's the maximum signal that will be seen off the side of a cylinder. Off of a cylinder, in fact. The largest signal to be seen off a cylinder is that signal directly off its side, or perpendicular to its side. Now, if possibly, let's say that cylinder had a flat plate on the end of it here, the end of it was actually a flat plate, then it's possible, if the flat plate is large enough, to get a much larger return off the end. But that no longer is a cylinder return. It's what we know as a flat plate return. And we'll have to analyze the flat plate a little bit differently later on. The point I'm trying to show now is just the cylinder. This is the backscatter pattern for a cylinder. It does vary as the cylinder rotates, or the aspect angle changes from cylinder to the radar. And a little knowledge of antennas related to beam width and so on, we would be able to say that there is a relationship between the length of the cylinder and the lobe width of the principal lobe of the pattern off the side of the cylinder. And the relationship is length is equal to wavelength over sine of the angle 2 delta. 2 delta being the main lobe width. Now, that's probably enough on the cylinder for the moment, I think. Except, looking at the length equation here, what kind of general information could we come up with? What kind of general information could we come up with from that equation? What's going to happen to the lobe width if, for some reason, the cylinder became longer? What would happen to that lobe width if the cylinder became longer? Well, what happens to the beam width of an antenna when the antenna diameter becomes larger? The larger the antenna, the narrower the beam width. It's the same thing here. The longer this thing gets, provided wavelength stays the same, it means this must become smaller. For this to get smaller, that gets larger. So for this to become smaller means the angle, 2 delta, has to become smaller, which means the lobe width is narrower. So the longer the cylinder, the narrower the lobe width. The shorter the cylinder, the wider the lobe width, the specular width, and of course consequently the side lobe widths. So the narrower lobe width represents a much longer target. And I want to illustrate that graphically to show you something that might be a little bit deceiving at times. We have to be careful here. If you saw an AGC record that had a lobe like this, and then you saw another AGC record that had, say, a pair of lobes, speculars that look like this, which one actually looks like the larger target? Which one actually would look like the larger target? Well, this of course looks bigger because it has bigger area under the curve, but in fact, this is the longer target. You find there is an amplitude difference here, and the lobe width being narrower says that this is a longer target than this one is. The narrower the pulse, the longer the target is. So in all probability, this is the much larger target. Now, in fact, we're getting much stronger signal back here than here. Normally on an AGC recorder, the amplitude information is logarithmically compressed. It's a log scale. And since it is, because of log compression normally seen, we don't see a great amplitude difference here necessarily, but in fact, if you would compute the amplitude difference, it could be several dB difference between those two. Several square meters of target area difference between these two. The pertinent point here, though, is that lobe width is not a lobe width is an indicator of the dimensions, but it's inversely proportional to the length. Longer, the bigger the target is, the narrower the lobe width becomes, and this is, of course, most significant. Well, I think that's probably enough for today. I wanted to introduce one other thought, and we'll just introduce it now and then we'll come back to it later. There are some mathematical equations available which describe the cross-sectional area of the cylinder, and we'll look at some of these equations a little later. But I want to show you, as we if we could go to our podium now and look at this chart, we'll see that the cylinder cross-section, this says cylinder sigma versus theta. Theta, you recall, is the angle from the radar line of sight to the perpendicular to the side of the cylinder. We see here that we have at 0 degrees, which is exactly perpendicular to the side of the cylinder, the main specular return. It has a width of 2 delta. The side lobe width of the first 2 or 3 side lobes is delta. That is half the width of the main lobe. Side lobes are half the main lobe. But you'll notice on this particular card there's a relationship also here between the amplitude of the peak of the specular return and the side lobes. For a perfect cylinder, a classic cylinder shape, we find that the peak of the first side lobe is exactly 13.3 dB down from the peak of the specular return. Now, that's pertinent information also. There will be times, perhaps, when you cannot see an entire rotation of a cylinder, but just the specular and maybe a couple side lobes. If you could measure very carefully the amplitude difference between the peak and the first side lobe, and you find it's about 13.3 dB, you could say in all probability that's a cylinder. The second side lobe is 17.8 dB down roughly, and the third side lobe is about 20.8 dB down. Now, that's significant because if we would look at a flat plate, for example, a specular return off a flat plate, we find the first side lobe is 17.6 dB down. There's a considerable difference. So if you had a pulse that was 17.6 down, a side lobe, you could say that's possibly a flat plate, whereas from the cylinder, side lobe's only 13.3 dB down. Now we'll have to look at the math expression for this a little bit, not go through it in depth. It's rather involved. But there are relationships between peak and amplitudes, between lobe widths, and several other factors here. And we'll consider all these, and we'll use all these in our analysis. It really doesn't pay to stick to one method in making an analysis of various targets. It just doesn't pay. You need to apply every method that you have available, every technique you know, and then weigh the separate results. You weigh them by, of course, assigning point values to the method that highest point value to the method you think is best for that particular situation, and lower point values to less accurate methods, but weigh all these and put them all together and come up with probably a composite value. Well, I think with that we'll conclude the discussion on the cylinder for the moment, and we'll pick this on up and expand on it a little bit more in the next tape and begin to develop from the cylinder. We'll take a look at the conic and put some pieces of the sphere on the conic perhaps, and then we'll put a cone and a cylinder together and see what we can make out of it and come up with some more composite shapes, which are generally what we see as we track these various targets. I think with that we'll conclude lesson number 6. In the past several tapes, carefully developing the radar equation, at least fundamentally so, and from the radar equation drawing out the radar cross-section. Explaining radar cross-section, we looked at radar cross-section as it relates to a sphere. The last lesson, we began to look at the cylinder. Now, I think about the only thing we considered on the cylinder really was that it acts like an antenna, as does every radar target, that the RF energy that's on the target that radiates from the target is a result of the energy that came from the transmitter antenna of the radar, that we have to treat each point on the separate targets, on the various targets, as separate antennas, consider the phase relationships of these various points, and determine what the cross-section area or the signal is that would be reflected back to the radar. Now, the 4 classic shapes that need to be considered, let me list them on the blackboard over here. There's 4 basic shapes that we need to consider concerning that radar cross-section in our analysis work, because virtually all targets are made up of some combination of these 4 basic shapes. Now, the first shape we've considered already in depth is the sphere. Sphere is the basic shape number 1. And the sphere we found out had a radar cross-sectional area, if we go over to the right a little bit, of sigma. Well, let me list these. This is shape, and the sigma, or cross-sectional area, in the case of the sphere, was pi times the radius squared. Pi times the radius squared of the sphere. That was the cross-sectional area of the sphere. Now, the cross-sectional area of the sphere we found out was not dependent upon the angle or the viewing angle of the sphere. It was not dependent upon the angle or direction that the radar was looking at it. As long as the target was in the center of the beam, the target presented this cross-sectional value to the radar, provided that the sphere was somewhat larger than the wavelength of the radar. I think we discussed in a previous tape the fact that as the targets become smaller and smaller in relationship to the wavelength of the radar involved, that the target begins to exhibit resonance characteristics. Now, as long as the target is somewhat larger than the wavelength of the radar, then these values, equations that we're putting on the board, do hold true. Now, a sphere, we said then, was a pi r squared. That is the cross-sectional area of the sphere. The second shape we considered, briefly, we'll have to consider it some more now, is the cylinder. Well, let's do that. Cylinder. And we hadn't considered the cross-sectional area of the cylinder yet. I'm going to just do something here that may not be totally proper. Let me just put an equation on the board, and I'll show you what the cross-sectional area of this sphere is, or cylinder is, and then I'm going to modify it a little bit and give you an equation that will very simply define the maximum cross-sectional area of a sphere. First, let me define a term. You recall, if we look at the side of a cylinder, the viewing angle, the radar is looking at it in this direction. We define the angle between the normal or perpendicular from the side of the sphere and the radar line of sight as being theta. Theta. Now the equation will use the value theta in it, and this is the value theta. It's the angle between the radar line of sight and the perpendicular to the side of the cylinder. Now the sigma for a cylinder as a function of the angle theta. Now, of course, sigma varies. As the angle theta varies, the radar cross-sectional area varies. As theta goes to 0, we found out we had maximum radar cross-section. So in this case, then, sigma as a function of theta is equal to, and I'm not going to develop this equation, I'm just going to give it to you, both barrels at once, and then we'll simplify it, is equal to 2 pi times the radius of the cylinder times its length squared, divided by the wavelength squared of the radar. That's the cross-sectional area, and that would be, by the way, the maximum cross-sectional area of a sphere. Of the cylinder, excuse me. But as a function of theta, we have to add more to this to modify it as the value of theta varies. So we have to multiply this by the cosine of theta times all this mess, the sine of the value 2 pi length over lambda times sine theta, all over everything in the parentheses here, which is 2 pi length over lambda times sine theta, and all that squared. Well, that's quite a mess, and that's, of course, far more than any of us want to deal with in trying to compute radar cross-sectional area of a cylinder as a function of aspect angle. Now, there's a little trick here, though. If we recognize what's in the brackets over here, we should recognize that the value here is the same as that in the denominator. So what we have, in essence, is the sine of a function divided by the function itself. A sine of a function over the function itself. Now, you might recognize that more conveniently in the form of sine x. X is this function divided by the value of x. Now, if you've had any differential calculus, one of the first things you recall going through your study of limits is that as x goes to 0, the value of this expression, sine x over x, goes to 1. Now, let's examine this. This whole term will go to 0 when theta goes to 0. The sine of 0 degrees is 0. 0 times this is all 0. So the sine of 0 is 0. In this case, when this goes to 0, the denominator goes to 0. So what we have is when the angle theta goes to 0, this whole term becomes 1. Becomes the number 1. Now, when will theta be 0? Theta is 0 when the radar is looking perpendicular to the side of the cylinder. You again recall the cylinder. Theta is the angle between the radar line of sight LOS, and the perpendicular. That's theta. Theta goes to 0 when you're perpendicular to the cylinder. Now, if theta goes to 0, this whole term becomes a value of 1, or goes to a value of 1. So we can take all this out and find out what the radar cross-section will be for a cylinder when we are perpendicular to the side of the cylinder, or the maximum cross-section. And in this case, all that term disappears. It becomes a value 1. 1 times all that is just the same as leaving that off. Now, when theta goes to 0, what does the cosine of theta become? Cosine of 0 degrees is 1. So this term goes to 1 as we approach the perpendicular, or the maximum cross-section of cylinder. So we're left with this simple little equation which describes the cross-sectional area of the cylinder. That is, maximum cross-section is no longer a function of theta. This now becomes sig max. Sigma max. Maximum cross-sectional area of a cylinder is 2 pi times the radius times the length squared divided by wavelength. Now let me check that. I may have an error. Right. Divided by wavelength, not wavelength squared. Divided by wavelength. We have to have now, sigma is expressed in what? If you recall, sigma is a measure of the effective cross-sectional area of the target. Now area is always in square units. If it's in meters, it would be in square meters. So if the radius of the thing was in meters, length is in meters, wavelength in meters, the result would be 1 length times the length squared would be some dimension cubed, divided by a dimension would be the dimension squared. So we have a proper dimensional analysis here. Pi times units cubed over units, or result is in square units. So sig max then for a cylinder is equal to 2 pi times the radius of the cylinder times the length squared divided by wavelength. So that then becomes the second shape, second classical shape, and this is the expression for the cross-sectional area of that shape. The third shape we're interested in will be that of a cone. Now a cone is a little more difficult as far as describing the shape is concerned, or cross-sectional area, mathematically. It can be done. There's an expression that describes the cross-sectional area of a cone, but I think probably right now, let's just leave off sigma. The cross-sectional area of a cone is a little more complex than a cylinder. It becomes I think a second-order Bessel function, and it's not simple. At least not to me, being non-mathematical. So cross-sectional area of a cone, let's just skip that for now. The cone has some unique patterns, some unique lobing patterns, and some unique characteristics which we'll take advantage of. But as far as cross-sectional area is concerned, generally, we don't analyze cones on the basis of its peak cross-section. At least for the more simple cases, we don't. The fourth classic shape is that of a flat plate. Now, a flat plate. What would be the maximum cross-sectional area of a flat plate? How would we compute the maximum the peak cross-section of a flat plate? Of course, we know that the intuition would tell us that as we looked at a flat plate, the peak cross-section would be when the radar is looking perpendicular to the surface. Let's say if I'd hold it this way, when the radar is looking right perpendicular to the surface in both dimensions, this way and this way. When it's perfectly perpendicular, we get a maximum return. Now, what's the cross-sectional area of that then? What's the cross-sectional area of that flat plate? I think we find out that the flat plate cross-sectional area is very similar to that of the antenna. The cross-sectional area of the flat plate is equal to 4 pi times its area divided by wavelength squared, which happens to be the equation for the gain of an antenna. And that's just exactly what we have with the flat plate. We've got a flat disc which looks like the front of a dish. It is. It's a flat disc antenna. And its cross-sectional area is equal to its gain as an antenna. Its gain squared. Its area. This would be the gain of this thing as an antenna, and I think I defined cross-section recently as being the gain of an object treated as an antenna times its area. So that, of course, would then result in area squared. 4 pi times its area squared over wavelength squared. And we'll find out again we'll have proper dimensions because area is given in square units. So square units to the squared would be to the fourth divided by something to the squared. Dimension squared would give us the cross-sectional area again in square units, square meters, whatever dimensions we're dealing in. So these are the 4 classic shapes. You're familiar with the sphere. You're somewhat familiar with the cylinder already. And the flat plate should offer no problem. And the cone is the one that really needs to be looked at in a little more depth, a little more detail. The cone has some unusual characteristics. And some of the unusual characteristics are, first, the pattern is not symmetrical about the perpendicular to the surface. Let me clean some of this off the board here. And let's draw a cone on the board and examine it. Okay, there's the cone. Now, first of all, we define the axis through the cone as being the longitudinal axis, or 0 degrees aspect angle. When we're looking at the cone from the nose, we're looking at it with an aspect angle of 0 degrees. Anytime you're looking at anything on the nose, it's 0 degree aspect. Now, a 90 degree aspect angle would be from this direction. With the radar sighted here, looking at the cone, we find the aspect angle 90 degrees. Now, where would we see the maximum cross-section or maximum return from a cone? Just look at that for a minute. Let's, of course, ignore for the moment the base. Let's not look in at the base. Let's consider that it's an open base or something. We're considering the side of the cone now. Where would I see the maximum cross-section? We'd see the maximum cross-sectional area at an angle which would be perpendicular to the side of the cone. The radar would have to be sitting over here, looking at the side of the cone, and there it would see its specular return. So the specular return would come off perpendicular to the side of the cone. Now, what would that angle be? What would be the angle between here and here? Well, we need another little more information. Cones are generally defined by 2 values as far as radar signature analysis is concerned. The one value is the slant length. That's the length up the side from the base to the apex of the cone. L is the surface slant length from this point to this point. It's not the height of the cone, which is from the center of the base of the peak, but from the edge to the peak is the slant height of a cone. The other dimension that's usually given, or value that's usually given to define the shape and size of the cone, is what's known as the half angle. The half angle is the angle between the longitudinal axis and the side of the cone. This angle right here is the cone half angle, and it is usually expressed as alpha, the Greek letter alpha, with a little subscript c. Alpha sub c is the half angle. So let's define these. We have little Greek letter E, which is the aspect angle. We have a little alpha sub c, which is now the cone half angle, and we have L, which is the slant length. Slant length, aspect angle, and cone half angle. Now, aspect angle, of course, is the angle at which we're viewing the cone. The specular return, let's suppose now I give you an alpha sub c, 20 degrees. I'll say the cone has a half angle of 20 degrees. What would be eta, the aspect angle, where we would see maximum cross-sectional return from the cylinder or from the cone? Well, it would actually be 90 degrees minus the half angle. So 90 minus 20 would be 70 degrees, would be the point at which we would see the maximum return from a cone. The specular return is 90 degrees minus the cone half angle. Now, let's just leave that for a minute then. And let's do this. Let's put a cone up here. In fact, let me use a model I have so we can turn it around a bit and examine it. Let's put the cone up here. Let's put the radar up here too and rotate this cone. Well, let me do it this way. Let's put the radar here, the cone over here. Now, the cone is a satellite traveling through space. And let's say as it travels through space and the radar tracks it, it's rotating end over end, like this. And the radar views it from different angles. Now, as the radar tracks this target and it begins to rotate, and we see it from different angles, let's ignore the base for the moment. What am I going to see here? On a AGC recorder or amplitude recording of the return signal strength of this target as time goes on. And let's just mark time here. Let's just put some equal time hex across the time base of our AGC or function recorder and say that at this time, time 1, let's say the target's pointed straight up. Okay, now, at point 1, the target's pointed straight up and is rotating in this direction. Let's have it go in that direction. It will rotate from this point to this point. Now, it rotates smoothly, of course. It will rotate smoothly and continuously. And when it reaches this point about right here, we'll find the radar will get a specular return sometime after time 1. We started time 1 straight up. So time 1, not a small signal perhaps, and slightly after time 1 we get a specular return. Now let me just draw the specular here and maybe 2 side lobes. Now you notice I'm going to draw 2 different amplitude side lobes, one smaller than the other. Generally you'll find on a cone one side lobe will be shorter than the one on the other side. So here's one specular. Now this thing rotates, comes on down, we don't see anything, and finally it gets down here. Well, let's put time 2 down here. Sometime just before time 2 we get the specular again. Now let me straighten that up a little bit there. Now we get the specular at time 2. Of course we're beyond the specular again. Now as it goes on around we don't see a side again. Ignoring the base return, we don't see its side again. We get all the way up here to time 3 now. We haven't seen any return at all between time 2 and time 3. Now when we get slightly beyond time 3, we get another return. We go on down here, we get just before time 4 now, we get another return. And on around again. We skip a whole time period from time 3 to time 4, and then time 4 to time 5. And going on and on, we continue to find this pattern. we find these are equal time intervals. Time 1, 2, 3, 4. Let's say they're every 10 seconds. 10 seconds between time intervals. We find for the cone tumbling end over end, if the radar is in the tumble plane, that the return pattern would be a group of 2, a blank, and another group of 2. Now we have a lot of information here. First of all, what can we say about the period of this thing? Well, let's define some things first. If we're looking at this, and we've got these time marks on the time recorder, time base of the recorder, and these lobes are coming along, looking at those lobes, we would probably say that they don't represent those of a cylinder. One thing about a cylinder, you'll find that the two opposite sides are parallel. And as motion is linear in time, the spacing of the speculars for a cylinder which is tumbling occurs on equal time intervals. Now that doesn't happen here. For the case of the cone, the speculars do not occur at equal time intervals. They're grouped together in twos. Now right here we see something's wrong. Something's not quite culture. Well, it's not really wrong. This is the way a cone behaves. Now, we can examine that thing, and we know, by intuition again, that it takes less time to go from this specular around to this specular when we're perpendicular to the side than it does from here to go around the base all the way around to the one on the other side. It takes less time to go around the nose to see speculars than it does around the base. So we can look at this and say, well, now these two are closer than these two. Therefore, probably the nose of the cone is right in the center. And that's true. The nose is between this point, between these two speculars. And going around the base takes longer time. So, right in between here, we have the base of the cone. Now, if we've got the nose and the base and the nose again, what is the first tumble period of this thing? What's the tumble period? The tumble period is the time between repetitive portions of the pattern. Now the pattern repeats itself right here in the center. The nose, it goes all the way over to here and we see the nose again, and from here on we see the same thing repeated all the way down the board. So the time between nose to nose is the tumble period. That corresponds to the time between these two speculars, because they're the same ones, these two, and the time between the center between them. So from here to here is the tumble period. That's the period of motion. How fast is that thing rotating? And that's the period of motion. Secondly, from this recording, we can come up with the length, the slant length of the cone. The slant length, let's call it slant height or slant length, is equal to the wavelength of the radar divided by the sine of the angle 2 delta. Same as it is for the cylinder. Same equation. The lobe width is directly proportional to, or inversely proportional to the length and directly proportional to the wavelength of the radar. So, we know now that this distance from the nose to the nose, whatever time interval that represents, in this case it represents about 20 seconds, represents 360 degrees of rotation. If this is 360 degrees of rotation, we can 360 degrees of rotation in 20 seconds would result in how many degrees per second? 360 degrees of rotation in 20 seconds, divide 20 into 360, I come up with 18 degrees. Every second of interval represents 18 degrees of rotation of the target. So all I have to do is come down here and measure the time interval of between the nulls of the main lobe and find out what it is. And let's suppose it's 1 second. If it's 1 second, that means 18 degrees. And I can plug in the sine of 18 degrees in this equation, determine the wavelength of the radar and put it in, and determine from that, calculate the slant height or slant length of the cone. So from that simple little record of tracking a tumbling cone, we've determined two things. First, the period. Secondly, from lobe width measurements, we've determined the slant height. So we know it's dynamics now. We know it's tumbling, and it's tumbling end over end. We know it's tumbling with a period of, in our case, 20 seconds. We've determined the slant height, and whatever it happens to be, we can easily calculate it. And a third value that can be measured here would be what? What other thing could we measure? Well, how about this cone half angle? You suppose the cone half angle has anything to do with the spacing of these speculars? It does. If this is the nose and this is the base, what's exactly between those two? Halfway between the nose. Let's move that down. We can see it all together here. That doesn't erase, does it? Here's the nose. Here's the base. Halfway between the nose and the base, of course, is a 90-degree aspect angle. Halfway between them is the 90-degree aspect angle. And I could go from here to here, find the exact center, and mark it. Let's say it's right here. Now, if this is the 90-degree point, which we've marked it's halfway between the nose and the base, what's the distance from here to here? Between that point and this peak. The specular came off of here. And we said the specular, or maximum cross-section, was equal to 90 degrees minus the cone half angle. So the angle between here and here is alpha sub c, the cone half angle. Now, all we need to do is measure the number of seconds in time on the time base here between the 90-degree point and the cone side specular. We compute the angle in degrees, and that angle becomes the cone half angle. Now you could have done it the other way by measuring from the nose over and had the complement, the 90-degree complement of the half angle, but it's easier to do it this way for me because the angle comes out directly. What we want, we split the distance between the nose and the base, and we're doing a lot of splitting here. We split the distance between the two closest speculars, that becomes the nose. Split the distance between the two furthest apart speculars, that becomes the base. Split the distance between the two, the nose and the base, and we have the 90-degree point. And from the 90-degree point to the specular peak is the cone half angle. So from this very simple little record, a simple track of one track, we have determined three separate functions, actually four, or values about that cone. We have decided that first, it's tumbling. It has a period equal to, in our case, 20 seconds. Then we said it had a slant height of some value. We didn't use anything in our example, but it does have some value we can measure by measuring lobe width. And we said it had an alpha sub c, some value. So we've determined that it's a tumbling thing, determined its tumble period, its slant height, and its alpha sub c, its cone half angle. And the slant height and alpha sub c completely define the shape and size of that cone. And that wasn't difficult to do at all, was it? So signature analysis, you'll find out, is really not that difficult. It takes some intuition and some reasoning here. But applying these basic principles, you're going to find out that in most cases your analysis isn't too difficult. It doesn't require a whole lot of effort to come up with some basic and realistic values for the parameters of the various targets you'll be tracking. It's extremely important, though, to have the cone very clear in your mind. You'll find the conic shape occurs very often in rocket bodies and rocket nozzles and nose cones and interstages between, let's say, a second and a third, or a third and a fourth stage of a launch vehicle. And all these things end up in orbit. A lot of them do. Some of the targets in orbit, we've got some of the targets that are cylinders with truncated cones on the ends. It's a cylinder with a truncated cone that's lopped off on both ends. And the base end has a couple of, well, actually more like this. With maybe 2 or possibly 3 rocket nozzles sticking out the base. And all these things appear as cones. You can see a conic surface here, one here, another one here, and then of course the cylinder surface there. And sometimes even looking in the base of these nozzles you can get some kind of multiple reflections that give you an appearance of a conic surface. So you have to understand cones, and you're going to find out in your analysis work now when you're tracking a particular target and looking in there, you'll find there's basic cylinder patterns, and a cylinder pattern, of course, is evenly spaced speculars. You might find that you're tracking along and you get a specular rise up out of the mud, a specular, 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 and so on. Now, you could look at that and say, well, those are evenly spaced. Since they are, I have a basic shape of cylinder. Now, if you look a little more closely, you might look in there and find, well, there happens to be a small specular here and here, another one here and here. Well, you've already identified the evenly spaced ones as belonging to a cylinder, so sort of just take those out. And now you see a pair here and a pair over here, but nothing in between. Well, that's very characteristic of a conic. Somewhere in here there's a conic surface. And cylinder speculars happen at the 90-degree point, at the 90-degree aspect angle. So the distance between here and here would be the half angle of the conic. The distance from that specular to that one is the half angle of the conic. And you know that around one end, this would be the nose then, there's a cone somewhere. So let's just put a cone up there. We don't know how long it is yet. We don't know if it's a complete cone or just a truncated cone, a partial cone. So we'll just attach a cone on there, measure its half angle and say, well, this is his half angle and this is his dimensions and so on. And then looking a little further ahead, we might find we see 2 little tiny ones down in here. And again way over here. These are the ones here say, well, there might be a cone on the other end. But it's not very high in amplitude. So maybe there's just a little, and by the way, the very close spacing of these says it has a very high cone half angle. So maybe it's just a little piece on here like that. And as you look at this, you begin to recognize various shapes that pop up in the pattern. Now, here's where a little intuition is required. You don't know if this cone is on this end of a rocket body or a cylinder. All you've done so far is identify the fact that there's a cylinder and a cone. Now, you're going to have to use a little common sense here once in a while. You could construct that shape if you wanted to like this. But do you expect that you would see up in space the peak of a nose connected to the base of a cylinder? No, in all probability, that conic that you see here would be either a base flare, for example, the inner stage between the rocket third stage and second stage, or more probably the nose, either a truncated or a complete cone. Now, you could use a little logic here. You've got a cone, you don't know which end to put it on. Is it on the base or the nose? Well, let's use a little reasoning. When a rocket is launched into space, you'll find associated with the rocket stages there's various pieces of hardware that turn out to be junk after it's all over. For example, the inner stage. You have a main stage, or let's say a second stage, a little piece of sleeving or conic or something is connecting a third stage on top to it. Now, when the second stage burns out, do you leave junk like inner stages attached to the third so the third can carry that extra weight on up? No. Normally all that's left behind is, or that can be left behind is. So rarely will you see a base flare on a rocket body in sky. Normally the inner stage, which connects it to the previous stage, would be left with that spent stage, fall back in the atmosphere, and the lightest possible weight is shot on up into orbit. So normally you can say, well, if there's a cone and a cylinder, probably this is a rocket body, and very possibly the cone is here on the nose. It probably would be. Well, it takes a little common sense here. We have to first become familiar with the various shapes we have. And once becoming familiar with the various shapes, we put these various shapes together and try to consider what they look like to the radar in various configurations. And then lastly, we have to apply a little common sense. Look at the AGC record or whatever function records you have concerning giving your amplitude information. Pull out the shapes that you can identify, and then try to construct them together in what you feel is a realistic, real pattern. Now, I think with that we should conclude. I'd like to suggest at this time that you read a little bit in your student handout booklet that came along with this course. We are summarizing the important points and equations for each lesson, for each tape, on a page in this booklet. And it wouldn't be worth your while really to go too much further without having a good review, or at least fresh in your mind some of these equations and summaries. So I'd suggest you spend a little time studying these now before we go to the next tape. In the next tape we're going to continue this. I think we'll put some various shapes together and begin to give them different motions. We haven't talked much about motion yet except the tumble motion, and I really haven't defined tumble yet. I'd like to define tumble, spin, precession, nutation, and oscillation, and see how they affect the radar return. Now, all these motions modify what we've seen on the board to date, and we have to be familiar with what the shape does to the pattern and what various motions do to the pattern, and also how the motions of shape affect the various lobing patterns. So I think with that conclude lesson number 7, and we'll take up next time. I think the last couple tapes we spent some time considering the basic characteristics of the cylinder, and I believe we looked at the cone also in little detail. We found out that some of the qualities about the cylinder, especially when it's tumbling in space. Now, we haven't spent much time considering target motions yet. I sort of assumed you know what tumbling was, and our discussion today will go on with that basic assumption. Of course, tumble being the end-over-end motion of an object. In the case of a cylinder, let's go over the blackboard for a minute. Let's summarize just exactly what we've had. I brought with me today some recordings from typical radars, and principally of the cylinder, and then some modifications of the cylinder. Cylinder with a cone and what we call a stepped cylinder. And I'd like to look at these examples after a little bit here, just to get an idea of what it really looks like on tape. So, recalling our radar situation, the radar looking out to some point in space, tracking a satellite. In this case, let's let our satellite be the rocket body, a rocket body that was associated with a payload that went into orbit. Now, in our case, our example, we considered principally the motion of tumble, although we didn't call it tumble. The end-over-end motion of a body, in this case, rotating like this, would be tumble, whereas the tumble axis, in our example, would be in and out of the board. That's the axis about which this object rotates. And the longitudinal axis through the body, rotating, in the case of the tumble, that line through the center of the body would define a flat plane, that plane being known as the tumble plane. So if the body rotates around a line perpendicular to its longitudinal axis, or axis of symmetry, that axis, long axis, will describe a plane, and you might just show it here as a big disk. Now, the radar would lie on that plane, and for our example, that's what we considered last week, the radar lying on the tumble plane, and as the object tumbled, rotated end over end, we would see at one instant at a time the side lobe or the main specular off the side of the cylinder, which would result on the case of a, let's say, a MIPR radar where the AGC level is recorded, At this point, a very high AGC level. And as time goes on, we'd see the main specular from the side of the cylinder. Of course, associated with that would be the cylinder side lobes. Now, as the cylinder continued to rotate, the other side, with its specular return, would eventually come into radar view. And as it came around, the radar saw it. With some time elapsed, we'd see the side lobes, and then the main specular again, and go on. Of course, that happens at very even intervals. Tumble motion is linear. That is, as time goes on, it just continues to rotate at the same rate. And every time it rotates 180 degrees around, we would find a nice return back to the radar. That's what we'd see on the AGC recording then. A series of evenly spaced speculars right on down the road. Now, we have some examples here today. We'd like to go over to our podium here and look at some first simple examples. We have here a typical case of a rocket body in motion. In this case, the motion is tumble or very nearly tumble. And if you can see that, what is represented here is time in this direction, and it's recorded along the top part of the chart. I think up here about about 1 second every 2 centimeters here. Approximately 1 second every, it'll be 2 seconds per centimeter in this case. 2 seconds every centimeter along this piece of graph paper. Along the bottom down here is recorded the AGC level from the radar. That's the automatic gain control. Now, of course, the higher the signal, the higher the AGC level. So down here is probably 0 signal to noise ratio, and as the signal increases, we find out that the AGC level increases to some higher value. Now, right here is a typical specular return, as you might see on an AGC recording. We see a specular return here. If I can get them all on the screen, there we go. One there. As time progresses, have another one. As time progresses, a third one. So what we know we have here right on this chart is one complete rotation of a cylinder. Now, we don't know this is a cylinder yet. I'm afraid I've jumped ahead here. The first thing we need to do to establish the fact that this is probably a cylinder is to measure the distance. If we had some type of measuring device, for example, a pair of dividers, and a pair of dividers is a must for you analysts, you take a pair of dividers and measure the distance between these specular returns. And you would see that the distance from this return to this one is identical to the next one, same as the next one, same as the next one. Well, we changed chart speeds here. Let's go the other way. This distance between these speculars is the same all the way down the road here. And by noticing that, first of all, that these specular returns or large amplitude returns are evenly spaced, we know that this cylinder must have, well, it's a fair assumption that it's a cylinder. That's a good start. It's probably a cylinder because principally only a cylindrical shape gives you consistent, evenly spaced speculars. Now, a cone can actually produce evenly spaced speculars when the radar is not in the tumble plane, but it can only do so for a very short period of time. If you have consistently spaced specular returns throughout a track, you can, with a reasonable degree of assurance, say that's the cylinder surface. Now, the next step is to identify these. Now, we know that at this point right here on the edge of your screen here represents one side of the cylinder. And let's just arbitrarily give that a value. We know if it's the one side of the cylinder, it has an aspect angle of either 90 or 270 degrees. So let's just say we don't know what the nose or the base of this thing is yet. Let's just write a value of 90 degrees here. 90 degrees. Meaning that this cylinder specular is looking at the 90-degree aspect of this, or the radar is looking at the 90-degree aspect of the cylinder. It's looking at one side. Now, we know that the next specular return would occur 180 degrees of rotation later, which would be over here. So this would be the 270 degree aspect angle. Now, we made an assumption here. We're assuming that we're rotating from nose to side to base to side back to the nose again. Now, if that's 90, that's 270. This must go around the other end back to 90 degrees again. Now, this is reasonable. We're not sure which end is which yet, but at least we've got to start here. Now, we know then that halfway between 90 and 270 would be 180. So if we had a pair of dividers, we'd very carefully measure in here, and we might draw a little mark and say, well, that should be about the 180 degree point. We go between the 270 and the 90, find a place right in the middle, make a little mark, and say that's probably the 0 degree point. And now, based on the information we've got from this record alone, we've pretty well identified this object as being a cylinder by virtue of its evenly spaced speculars. The speculars are, of course, recurring here, here, and there, representing 360 degrees of rotation of this cylinder. Now, the next thing that can be done from this is, well, we can come up with a tumble period. We can actually measure the time interval between this specular all the way over to this one where the pattern repeats itself again, begins to repeat itself. We have one side, the opposite side, and the first side again. And the total time elapsed from here to here represents the actual time of rotation, well, the apparent time of rotation of this body in space. And all we need to do is go up to the timing track up here, just count the number of seconds that has elapsed across the top. And, of course, you have tumble period. So you've got two very important pieces of information already. Number one, this is probably a cylinder. Number two, it's probably a tumbling cylinder, and its tumble period is so many seconds as measured off the top here. Well, that's a good start. In fact, that's an excellent start. One more piece of information that can be obtained from this particular record, and it can be done by two methods, and it probably should be. Number one is there is a correlation between the peak amplitude of this signal, the specular peak amplitude. If your radar signal system were calibrated and you knew what how many dB signal to noise each one of these vertical increments represented, you can translate that to the radar cross-section. Now, of course, you need to understand the radar equation to do this. We need to convert the cross-section here, or the dB signal to noise, along with the range measured at this time, and of course we have to measure the time up here to find out what the range was at that time. Using the range at this time, this signal to noise ratio, we can solve the radar equation and come up with the value of radar cross-section. Now, radar cross-section is related to both cylinder length and diameter. Now, I have some charts and graphs which we'll use in a later course showing how these are related. Good assumptions can be made here, reasonable assumptions concerning the length to diameter ratio of these cylinders. Most of these cylinders in space have a length to diameter ratio of in the vicinity of 2 or 3 to 1. Let's say a 3 to 1 ratio. We could assume a length to diameter ratio of 3 to 1. And we'll find in our cross-section equation for a cylinder that the length is a predominant factor, so the diameter really doesn't contribute that much to the total signal here. It's more, the length itself is a more significant factor. As you recall in the equation, the radius, it was in the numerator, the radius times the length squared. So the length has a much greater contribution to the total amplitude here, so it's reasonable to assume, let's say, a length to diameter ratio of 2 or 3 to 1. And knowing the ratio 2 to 3 to 1, we can then convert cross-section here by solving the radar equation. Once we get cross-section, convert it to some actual length. There's a direct relationship between the amplitude here and the length of a cylinder. Now, another thing we talked about in the past tape was that there's a relationship between the width of this little lobe here. Now, Probably on the television you can't see it too clear, and you can't see it too clear with the naked eye either, but it's there. If you had a magnifying glass and a very fine-pointed dividers, you could actually measure at the base of this lobe the width of that lobe. Convert that width to a time interval. Maybe it's 2/10 of a second. And as you recall, we can convert the total time, the period here. Period, we said, represented 360 degrees of rotation. And maybe that took 20 seconds for 360 degrees of rotation. And if we found out that the width of this little lobe was 1/10 of a second, we would know then that the width of that lobe in degrees was 1/200th of a degree. Well, no, that's not right. It would be 20, you divide 200 into 180 degrees. If it's 20 seconds per 360 degrees, let me back up and get this square. If it's 20 seconds for 360 degrees, and it's 1/10 of a second for the width of the lobe, we could divide 20 seconds into 360 degrees, which would come out 18 degrees, and then multiply that by 0.1, would come out 1.8 degrees, and we could come up with the width of the lobe. And as you recall, and let's go back to the blackboard just for a moment here. Recall that the equation for the length of a cylinder, if we have a cylinder here, you recall off the side of the cylinder was the main lobe and then side lobes. Recall that the angular width of that lobe we labeled as 2 delta, some angle 2 delta. We said that the width of the side lobes, first 2 or 3 side lobes on either side, has a value of delta, whatever that length is, or the width is. Half the width of the main lobe. We also, you recall, said there was a relationship between the lobe width and the length of the cylinder. This is nothing more than antenna theory. The longer the antenna, the narrower the radiating lobe off the side. So in our case, we said the length is equal to the wavelength of the radar, and for a MIPR radar or C-band, that's approximately 2.1, 2.2 inches. Length or wavelength divided by the sine of the angle 2 delta. Sine of the angle 2 delta. Now you don't have to take the sine of the angle if you don't want to. Most of these angles are up under 20 degrees, and you know that the radian measurement, converting the angle to radians, is equivalent to the sine of an angle up to approximately 20 degrees. At least up to 20 degrees there's less than just 1 or 2% error. So just the wavelength divided by the sine of the angle 2 delta, or the angle 2 delta expressed in radians. Sine, of course, and the radians being almost the same for any value under 20 degrees. So we've measured the lobe width on our visicorder, our amplitude recording. We knew the period of the motion. We said that represented 360 degrees of rotation. We measure the time of the lobe to find out how that corresponds to the period. Convert that to angle, to degrees or radians, plug it in, the simple equation, and out comes the length. Very simple. So we found now, just briefly, there's 2 ways so far to find the length of the cylinder. Now I haven't spent much time on the one yet, which is the amplitude method. It's not quite as accurate generally, but sometimes it's the only way. Sometimes you cannot get a proper lobe width measurement. There's a relationship between the amplitude of the signal and the length of the cylinder. The longer the length, the greater the amplitude. And of course, the bigger the diameter. Of course, the larger the amplitude also. So, that's a good start. We've decided that from that simple AGC record, which we've displayed on the podium, on the overhead camera, we saw the repetitive speculars evenly spaced, and by that we said then that this was a cylinder. We have measured the period of it by comparing the, looking at the time spacing between every other specular and the time track on the chart. We looked at the amplitude, and we haven't gone through that yet. I'm going to have to get some charts and graphs out and show you actually how to compute length and diameter from amplitude. Then we went to lobe width and measured the lobe width. And from lobe width measurements, if the radar is in the tumble plane or near the tumble plane, we come up with some very accurate values for cylinder length. Do something here. If we go back to our podium and look at this chart, we have here the specular returns. We said here was 90 degrees, 180, 270, 0, or the nose of the thing. And now we're just guessing as to which end is the nose. We probably have to have a little more information to decide which end is the nose and which is the base. But I'd like you to look at something very carefully if you can. Let me find the proper specular. Here we go. Let's use this one right here. It's not too clear, but if you would look very carefully at this specular, perhaps you would see that it's not as smooth as it ought to be. It doesn't smoothly rise up and come back down again. If you could see that in greater detail, you'd see it's kind of ragged toward the top. And the same with this one. You see there seems to be little notches in the top of the specular. And the same over here at the 90-degree point. Now what we've done to amplify this is run this chart at a little bit higher speed. And over here we have an expanded scale. You can see the time increments expanding here. That means the chart's running faster. So what we would expect to see would be the same lobe pattern, but in this case now, greatly stretched out. Now here's the specular return again. And if you would look at the peak of this, you'd find the specular doesn't come up to a nice sharp little point. There's actually, in this case, two little notches in the peak. And if we go on over here to the next one, which will be way over now, looking at that thing right there, it doesn't come up like we sort of want it to. It kind of comes up and is a little jagged at the top. Well, now that's significant. That's not without significance. If we go over to the board again, let me illustrate, if I can, just what it is we're seeing. We're not seeing a specular return that has nice side lobes, comes up to a nice peak, and back down again. We don't quite see that. Instead of that, and let me simplify it a little bit, we actually see side lobes, and then as the specular comes up, instead of continuing over smooth, we see maybe a notch. And I'll simplify this a little bit to illustrate the point. We see here a little notch in the side of that specular where we would think we should see a nice smooth specular return. Well, that notch is very, very significant. That notch is a key signal, a very key signal in our analysis. It tells us that instead of being one surface reflecting back, there's something else that's reflecting a signal back at that same point. And what we have here is actually two separate surfaces returning a signal to the radar, and as the relative spacing or distance of these two surfaces change relative to the radar, there's a phase reversal, a 180-degree cancellation of the two signals because they're 180 degrees out of phase. Now this can be produced by what's known as a stepped cylinder. And let me draw a cylinder here. And on the end of that cylinder, let's put another cylinder, but of a little bit larger diameter. Now that's a stepped cylinder. We have parallel surfaces. This surface has a specular and this one comes back. Now when the radar illuminates this from the side, we're going to find out that both of these surfaces send back a specular return. Now of course, I don't have it drawn too well to scale here. In fact, the distance would be, of course, much greater here, and the radar energy would come up, strike that, and come back to the radar. Now, here's the problem. One of these surfaces is probably larger than the other. Therefore, the signal from that surface would be probably the major contributor to the signal coming back to the radar. But notice here with this little smaller amplitude signal coming back. what would the phase, the RF phase value of this signal coming back be relative to this signal if, for example, the distance from this surface back to this surface were 1/4 of a wavelength? Let's suppose this back reflecting surface is 1/4 of a wavelength further away from the front surface, which is radiating back to the radar. Well, the RF energy would have to travel an additional quarter wave in and an additional quarter wave out, putting it 180 degrees out of phase with the RF signal coming back from the principal surface. Now what's going to happen? At this very instant, at this very point in the rotation of this cylinder, this signal would cancel from this one. And that would produce, back at the output of the radar, a signal something like this. We'd have the nice big specular return, which is this, and its amplitude would be modified by the presence of the little one. Now we don't see both of them together. We can't, because they're both coming back in the same direction, and all we see is the total signal entering into the antenna and being recorded on the recorder. The total signal is summed and displayed. But how it's summed, if they're 180 degrees out of phase, they'll cancel. They'll cancel, or the smaller will at least subtract that amount from the larger. So we'd find then that this null, from here down to here, wherever the distance is from here to here, that dip, that amplitude represents the amplitude of this thing at whichever point it's canceling. So the notch is very significant. The notch always very loud and clear says multiple surfaces, stepped surfaces. So in this case, with the record we have on the podium, we can pretty well say that this thing is composed of at least 2 parallel surfaces, one diameter cylinder and another one. And that's not unusual. This is very often seen on many rocket bodies up in the sky, and also on many of the satellites. Multiple surfaces is not an unusual effect. For example, I have here a recording, an amplitude recording of an Agena satellite, And one of the characteristics of the Agena, if most of you are familiar with the Agena has a main body which is some approximately 5 foot in diameter, with whatever's on the nose of it. Let's just put a truncated cone on the nose. The base of this thing, Agena, stepped in a little bit, and there's a structure coming out here. It may be longer, it may be shorter, and the rocket motor sits out the back. Now I don't have this drawn exactly to scale, but you see the principle involved here. When this Agena-type satellite comes flying by the radar, let's say it's Earth horizon stable, which means as it flies by, this thing is pointed directly towards the horizon ahead. So as it comes over the radar station, at this point we would see the radar the broadside of the Agena. Well, what type of signal would you expect to see? We have stepped surfaces, and at this point we should expect to see a large broadside specular with a notch. Now the notch may be deceptive. For example, in the case of the Agena, this surface is much larger than this little surface. And consequently, the little notch is not always really significant. In fact, sometimes it might produce just instead of a nice symmetrical broadside, we might see a broadside that comes out just a little bit. You might see just a little hump there. Something that would prevent it from being quite symmetrical or perfectly symmetrical. And if I find it here, if we look at our podium again, here's a typical return from an Agena. Now, this is a different type of recording. This recording is from a different radar, from the Trinidad type of radar. And what is being displayed on your camera right here is the different receivers. For example, this portion of the curve up here, this being the baseline, of course here's the timing, from this being zero signal level, this being maximum signal, this is the received signal in the vertical channel of the radar. That is, the radar's got two receive channels. It's got a channel for the vertically polarized energy and a channel for horizontally polarized energy. So what is seen here is the vertical received signal and the horizontal received signal. Now, in the case of the Trinidad radar, these individual amplitude returns, which are 30 pulses per second, there's actually, if you could look at it real close, you see a series of little lines running up and down, which are the instantaneous video pulses. The video signals are directly recorded on this visicorder 30 times a second, and the vertical and the horizontal amplitude is actually converted from an analog to digital converter, sent to the computer, where the computer solves the radar range equation, and out comes radar cross-section. Radar cross-section is recorded up on the other half of the chart. And in this particular example that I have, cross-section is not on here, but another receiver channel is, so I'll not show it. But this indicates, by the way, or what point we're driving at, a typical Agena record. We get on track, near the horizon, we don't see much signal. And as the track progresses, the Agena rises up over the horizon, we begin to see some of the side lobes from the cylinder portion and around the nose. Well, of course, we don't see the nose directly in this case. And then we get up here to a ways, and we find an increase in the lobing pattern. Lobes get narrower and more complex. And there is, by the way, around the nose of this particular example, a slight conic surface. The conic surface produces, but since it's very short length, produces a fairly wide and low amplitude lobe. And the conic lobe is actually buried in here. It's buried in here. You can see the baseline of these little lobes increasing. So there's actually a small wide lobe in here, which has superimposed on it the side lobes from the cylinder return. This is the cylinder side, the main side lobes, and then the smaller ones. And they're superimposed on a bigger, lower amplitude, but wider lobe from the nose conic. So you could sort of graph in here a wide lobe, find the center, and that's where the conic surface would be. Now, I'm getting a little ahead of you here, but we're going to get into that in great detail in a little bit. But as we approach the main cylinder specular, it's probably more pronounced down here in the horizontal channel. In the horizontal channel, you'll find that this lobe, it looks like a nice specular, but it's not symmetrical here. In fact, if you look very carefully, you would see right here a little bit of an indent. Right in here, a little bit of an indent. And you see the lobe rises sharply, right, goes over the peak, but then it seems to stretch out on that side. It stretches out a little bit from relative to that side. And that little distortion right here is seemingly insignificant, it is, tells you that there are multiple reflecting surfaces. Now, one of them is not very big, but it's there. And then, of course, as we pass through the main specular, we begin to see the side lobes on the other side of the pattern. Now, I've got to roll this chart up and get it out of the light, because it'll last about 5 minutes under these lights and go absolutely black. Well, I think that's a good introduction then to the actual use of this. I've got a couple more illustrations I'd like to use here. Now, let's go back to the board first. Let me clean some of this off. And I think you've seen the effect here. Now, in this case, I'm going to leave this cylinder here, this Agena here, for a moment. Let's say that this is the Earth. If we can see just part of that. And of course, the flight path of the satellite, if it's Earth stable, that is, a horizon stable, it will just fly along over the surface of the Earth. Now, if the radar is sitting here, and the target passes at PCA, it doesn't have to be straight overhead, it could be some lower elevation angle, but as it passes the point of closest approach, which is known as PCA, if this were horizon stable, we should expect to see the main specular off the side of the cylinder at that point. Now, let me move the radar over here a little bit. Let's say the radar is here, and this thing has just come up over the horizon, and we're tracking it now at this point. Looking in this direction, we'd see something around the nose. And as it continues to come closer, which is in effect the radar being under here looking up, it'll eventually reach a point where just before PCA, it will see the broadside or the specular return from the little conic surface. And I showed you that on that chart. The next event would be as it passes overhead, and let me show that by moving the radar, seeing the big cylinder broadside. Now, this being the major source is going to be the greatest contributor to the signal coming out of the radar. But there is another smaller surface back here which also radiates. It reflects straight off the side. And it will result in distorting the major lobe. It will result in a notch or some type of distortion in the major lobe. And of course, as the radar goes on, or as the target goes on, the radar is looking up the tail end of this thing now, it would see some complex pattern around the rocket nozzle. And it would be impossible to see a little return off the nozzle here. It's possible to look in the nozzle, reflect off the inside back surface and back out again and get a little lobe structure there. And all this can be taken apart and analyzed. The shape and size of the nozzle, the length and diameter of this can be assumed or determined. The diameter and length of this can be determined. The length of the conic can be determined. Conic half angle can be determined. And from the diameter of this and the length of this, with its angle, we can use a little geometry and come up with the diameter of the across the nose. So all this information's here. And hopefully we'll have a little time to spend looking at some of this a little later on. Let me use one more illustration, and I think we'll quit on this tape, summarize here in a moment. One more illustration. I have one more record here of a much smaller target, and you'll be able to see that by the amplitude, relative amplitude comparison, but it has a very interesting pattern. Let me move it right there. Okay? What we have here is the return from a fairly small rocket body. Now, if you would look closely, let's say right here, you'd find there's actually 3 speculars involved. There's a tall one, a middle-sized one, and a small one. And then going over to the other side here, see a small one, a middle-sized one, and a larger one. Actually 3 little lobes in a row. There's 3 here, and they sort of point up this way. High, medium, low, low, medium, high. High, medium, low, low, medium, high. And it just continues to repeat itself right on down the record. When we get over here where we have a little higher signal strength, in fact, way over here, we can see these 3 lobes very clearly. High, medium, low, low, medium, high. Now, the first thing to do in a case like this is you know that something's happening. Something's happening over and over and over. We've got a pattern here and here and here and right on down the record. It continues to repeat. But there's a little something here. We've got 3 lobes instead of 1. Now, in this particular case, the first thing that has to be done is which of these correspond to a cylinder, or do any of them correspond to a cylinder? And the first thing we need to do to find that out is to find out, are there speculars here that occur evenly in regard to time spacing? So what we would do, we'd say, well, now, this and this maybe look like the cylinder side. Maybe the 2 largest ones look like the cylinder specular. And I wish I'd brought a pair of dividers today. If we had a pair of dividers, we would set one point of the divider on this specular, right here, and the other point on this the next tall one. And actually set the dividers to measure that distance. And then pick the dividers up and measure from this tall specular and see if it hits this tall one. Now, if it doesn't, that says that this is not the cylinder specular. But if it does, if the distance from the tall specular to the next tall one is the same as from this one to that one, we could probably mark those as being the ones from the side of the cylinder. Now, let's do this. Let's say that this is the base area of a cylinder. This is one side. You go around the base to the other side. And from here, Oh, a gentleman just brought me some dividers. Let me show these. Use these. That's good. Let's do that. Let's just take a pair of dividers here now. We'll set the point right here, and the other point there. See, now, I should be able to just flop that over, and if I'm lucky, it'll fall right on the next specular, which it does. From here to here, and from that specular over to the next tall one. So we can see it does match. Now suppose I wanted to try this. Suppose I took the middle-sized speculars and say, well, maybe those are the cylinder. If that's the cylinder, when I flop this over here, it should hit the next one, and there's nothing there. It's empty. There's no specular there. So that's not the cylinder specular. So you have to find the ones that are evenly spaced. From there to there, from there over to there. So that's cylinder. Now, if that's the case, the next thing to do is to say, well, probably then, now remember we have to use a little intuition here. We've got to use a little common sense, this part. We have to say that what type of shape would possibly be up there in the sky? And of course this comes from a little knowledge of what actually is there. In this case, I would recognize this immediately as a small rocket body. A small cylindrical tube with a nozzle at one end and probably a conic truncated cone on the other end that's used with the satellite to put it into, to actually inject it into orbit. There's always a rocket motor with the satellite somewhere. It may be an integral part of the satellite or maybe a separate motor. In this case, we can say that possibly this is one side right here. Let me use the other pointer. This is one side. Go around the base to the other side, and from this side we go around the nose and see two little conics to the nose, back, and to the other side. And let's go over to the board very briefly. Put what this probably would be on the board, and we'll summarize and conclude Lesson 8. In this particular case, what is probably being seen is, we said first, a cylinder. So we just draw a cylinder. Now we saw from the 90-degree point and the 180-degree point two speculars. Now this degrees is the aspect angle, the radar viewing angle measured from the nose. So here's the longitudinal axis. This is 0 degrees, 180. We said that we saw, as we went from the nose, two little speculars coming in maybe from this angle and from this angle. One of these is a little truncated conic on the nose. It's truncated, it doesn't come to a point. This is actually the adapter here now, and the satellite was attached to the adapter. So we would see a broadside return out of here, a big one out of here, and where would we see another one perhaps? Another cone? Well, there's another cone all right, but actually it's the rocket nozzle. If you would have looked at that very closely, would you find that the small one was actually fairly wide in width, and that could come from a slightly curved surface. There's actually a specular return out of here, but it's a little wider because of the curve. It seems the curve would sort of stretch it out a little bit. So looking at the target from this direction, we'd see a small specular here and another one here and then the big one. And back on our overhead board here, let's look at the chart one more time. We see the side, the nose conic in the center, and the little shorter but fairly much somewhat wider lobe down here is probably from the side of the rocket nozzle. So we'd see the cylinder side, the nose conic, the rocket nozzle, go around the nose and see it from the other side. Rocket nozzle, nose conic, cylinder side, and around the base we didn't see anything. That is, going around the nozzle end. Now normally when you go around the nozzle end, the base end, you see a rise. You see what looks like a lot of noise in here, but you can see the amplitude here is a little higher than it is going around the nose. And generally because this is more of a noisy type surface, a noisier type surface, it does send some signal back, but it's rather hashed up because it's in effect multiple surfaces and fairly small, and we get sort of a rise in what looks like the noise level. But this is characteristic of the base, the nozzle end of many rocket bodies. And with that, I think probably we should conclude tape number 8, I'd like to again ask you to look at your handout material, become a little bit familiar with the illustrations and equations there, and we'll continue with this, of course, in lesson number 9.